Guy Barrett teaches this Docker Containers and Kubernetes Fundamentals course for beginners. Guy is a developer and trainer with more than 25 years of experience. He is a Microsoft MVP, frequent conference speaker, and was the leader of the Montreal.net user group for more than 23 years. All this is to say, he is the perfect person to teach you about Docker and Kubernetes.
Welcome to this Docker Containers and Kubernetes Fundamentals training course. My name is Guy Barrett, and I'll be your host in your learning journey into the amazing world of containers. I'm a full-time trainer with a developer background, and I'm based in Montreal, Canada, and that's where my strange accent comes from. I'm certified on Kubernetes and also on Terraform, Azure, AWS, and Google Cloud. I'm very honored to be a Microsoft MVP in the Azure expertise and a DigitalOcean navigator. You can reach me via the contact page and on Twitter. What should you expect from this course? You will not become an expert just by taking this course. This is an entry-level course that will provide you with a strong containers and Kubernetes foundation, and you'll gain enough knowledge to make sound decisions at work or in your projects. Throughout this course, you will find lots of hands-on activities to practice what you've learned. You will use Docker and Kubernetes locally on your PC or Mac, so there's no requirement to have an account with a cloud provider. Are there any prerequisites for this course? Not really. If you're a developer, a DevOps specialist, an IT pro, or even a technical manager, that's totally fine. No previous Docker or Kubernetes knowledge is required. We will cover a lot of ground. You will learn about containers, Docker, and the Docker registry. You'll learn about the Kubernetes objects like pods, workloads, and services. That's a lot of material, and the goal here is to get you from zero knowledge to a Kubernetes ninja. Well, at least provide you with enough knowledge to aspire being a Kubernetes ninja. I want to say a big thank you for learning Docker and Kubernetes using this course. If you like the course, you can help me by making a small donation. This is the link to my Buy Me a Coffee page. You can of course buy one of my other courses where you'll learn to run containers on different cloud providers' services and use a managed Kubernetes cluster in the cloud. And finally, I wish you all the best in your learning journey. Let's see how to set up your laptop or PC for this course. You need a laptop, PC or Mac, with either Windows 10, Mac OS, or Linux. If you have a Mac with an Apple Silicon, most tools should run perfectly. I will use Visual Studio Code with the Docker extension to help build, create, and run containers. VS Code is a free IDE that runs on Windows, Mac, and Linux. On Windows and Mac, you'll need Docker Desktop with Kubernetes enabled. On Linux, refer to the documentation on how to install Docker and Kubernetes on your distro. You'll need a Docker Hub account and a few easy-to-install tools. Refer to the setup instructions located below this video. The lab files are located in a Git repo on GitHub. Simply open this URL in a browser. Click on the Code button. If you have Git installed on your machine, you can type git clone with the link displayed here. And if you don't have Git, simply click on the Download Zip button to download the code as a zip file. Let's talk about the microservices concepts. If we head to Wikipedia and take a look at the definition that we find over there, it says that it's a variant of the service-oriented architecture, or SOA, a structural style / architecture, and that it arranges an application as a collection of loosely coupled services. So instead of a large monolithic system, we have multiple smaller pieces. In a microservices architecture, services are fine-grained, meaning that each of them have their own responsibilities, and the protocol used are lightweight, like an API exposed over HTTP or gRPC, for example. If we look at the monolithic architecture, these systems were usually built as one single unit. An IDE would group multiple projects, and we would compile the whole thing as one single unit. They were also deployed as a single unit, so we would need to copy everything, all the files on a server. And if we had to scale the system, we had to spin a new VM and deploy the whole system on that VM, and same for a third and a fourth server. An example of such a monolithic architecture is a three-tier application. Even though the system was clearly separated into layers, it was all tightly coupled. From the web project, we had to make a reference to the business layer project, and the whole system would run in the same address space. With microservices, we break our big system into smaller parts, each with its own responsibility. So let's say we have a class that deals with identity in our business layer. We can extract that code and place it in its own microservice. We can then scale each of these smaller pieces independently from each other. There's no strong bound since we expose functionality through an API. They can be written by smaller teams, and each can use their own programming languages like Go, PHP, C#. And domain-specific data can be stored in separate databases. So the way we would deploy a monolithic system is by deploying everything on a server, all the DLLs, files needed to run the system. We had to scale, deploy everything on more servers. Now let's compare that to microservices. Well, microservices are deployed independently. Each can scale independently also. Need to scale back one service? No problem. So if you have an existing monolithic system, how can you transform it into a microservices architecture? Well, you need to break it into small units, like the code that dealt with the identity in our business layer. Martin Fowler, author of the Patterns of Enterprise Application Architecture book, documented a way to achieve such a transformation using the strangler pattern. Let's say our identity code is here in the legacy system. We can place a facade to route the calls to it, migrate the code, and have the facade route the calls to the new microservice at some point. As we go, we will end up with less code in our legacy system, and when the migration is done, we can get rid of the facade. This pattern is very useful, and you can learn more about it using the link in this slide. And this concludes this lecture on the microservices concepts. Let's talk about microservices anti-pattern, because it's not all rosy. I know, It's kind of strange to talk about what can go wrong right away, but I think it's very important. First of all, it's not some kind of magic pixie dust that you can sprinkle on top of an existing system and boom, you get a beautiful microservices architect system. It takes effort and maturity to achieve this. From one monolithic system, you'll end up with a bunch of smaller pieces, and that can add extra complexity. A change to a microservice can have a domino effect and take your system down. And what about securing all of these microservices? It's also essential to use or introduce new processes in the organization, like DevOps, CI/CD, and testing. But be careful and don't try to implement everything at the same time. It's a recipe for disaster. Take it step by step and make sure you have metrics in place to validate each of these steps. And this concludes this lecture on microservices anti-patterns. Let's talk about the microservices benefits and drawbacks. Since each microservice runs in its own address space, there are less chances that if one of them goes down, it takes the whole system down with it. A microservice runs on open source technologies, so there's less vendor lock-in. Since they are smaller, in most cases, they are easier to understand, and that makes them faster to deploy, and also easier to scale. Like we saw in the anti-patterns section, there are some drawbacks. Complexity is added over monolithic systems to resolve their complexity issues. So make sure your team is well trained and has made some proof of concept, and make sure to start small, adding one piece at a time. Testing might appear simpler since there are less functionality in a microservice to test, but make sure to test the whole system. Deployment may appear simpler, but one update can impact many microservices and have a terrible domino effect. Ready to manage multiple databases? Calls between microservices will go through APIs, and this will add a bit of latency to all calls, so make sure you test for that. Pesky transients error will appear. You'll make a call, and it will fail, but try again 50 milliseconds later, and it will work. So make sure to implement some retry strategies in your code or by using a service mesh. Instead of one big point of failure, you'll end up with multiple ones. Can your system survive if one microservice goes down? And what about security? Are you okay if all these microservices can see and talk to each other? So yes, complexity is introduced for solving complexity issues. And this concludes this lecture on the microservices benefits and drawbacks. Let's now understand what is cloud native. You may have heard the term cloud native before, but what it is exactly? It's a way to architect and build complex systems, taking advantage of modern development practices and the use of cloud infrastructure. If we head to the Cloud Native Foundation website and look at the definition, we see that it's quite a long one. So let's break it into smaller parts. Cloud Native uses containers, service meshes, microservices, immutable infrastructure, and declarative APIs. We'll cover containers, service meshes, and microservices and the concept of immutability in this course, but not how to build APIs. Immutable infrastructure means that we usually never update something, but we replace it with a newer version. Loosely coupled systems mean that the functionalities are exposed through APIs. Observable with the use of metrics. Creation and updates are automated. And instead of making changes once every 6 months, we deploy high-impact changes on a frequent basis. And finally, we use a series of open-source projects to run our system. When the CNCF says to use open-source projects, they are not kidding. This CNCF landscape graph shows a ton of open-source projects that you can use, but don't worry, you don't have to use them all. The challenge really is to identify which one to use in the context of what you want and try to achieve. And this concludes this lecture on Cloud Native. Head to the CNCF website for more info. Let's go deeper in the Cloud Native concepts. Cloud Native is about speed and agility. The user wants new features right away, without any downtime. And the business wants faster release of feature to stay competitive. A cloud-native application architecture starts with clean code. Using domain-driven design techniques, microservices, and Kubernetes. This course is all about microservices and Kubernetes. Feel free to explore the concepts of clean code and DDD on your own. With Cloud Native, we need to change mentalities. Infrastructure becomes immutable and disposable. It is provisioned in minutes and destroyed as fast. It is never updated, but it's replaced with newer versions. Traditionally, we would care about our virtual machines. We would patch the OS, update the apps. With containers, we create newer version with the software updates, destroy the previous running ones, and replace them with the newer ones. So the containers that you'll run will be more like cattle than pet. Of course, this cloud-native thing is a lot easier when starting a new project, a blank page or a greenfield. However, it's still possible with legacy projects. I really like the Cloud Native Foundation Trail Map because it breaks the journey to Cloud Native into smaller, measurable objectives. You can set your own performance indicator to measure each steps to ensure a smooth journey. So let's take a look at the first steps. Your team must first learn how to containerize your application. The developers and the IT pros must know how to deploy and monitor containers. You need to automate deployment through the use of continuous integration and continuous delivery techniques and tools. You need to use an orchestrator like Kubernetes and maybe deploy your application using Helm charts. Then you need to add observability so you can understand what's happening in your Kubernetes clusters and be reactive. Use tools like service meshes to provide more functionalities inside your cluster. Implement security through policies. And wow, these were just the first 6 steps. Now, understand that you don't have to implement all of this, and especially not at the same time. I really like this trail map because it breaks the journey into smaller steps that the management can understand and measure. And this concludes this lecture on the cloud native concepts. Let's take a look at the CNCF website. The website is located at cncf.io. And from there, you can take a look at the various projects maintained by the CNCF, information on how to get certified, community information like the conferences that the CNCF organize each year. So let's go back to the projects menu. And you'll notice that projects are categorized in 3 categories: sandbox, incubating, and graduated. Let's click here on this, the second menu here. And let's scroll down to the bottom. And here you get the information about the meaning of these 3 categories. And basically, that's their maturity level. Sandbox projects are mostly newer projects, while graduated projects are projects that conservative enterprises are more likely to use. So let's take a look at the graduated ones. We found here Kubernetes, Helm, Jaeger. So let's click on Kubernetes. And basically that will show you the project website. Let's take a look at the incubating ones. Here we find Linkerd, gRPC. Let's click on gRPC. You can get more information about the gRPC. All right, let's go back to this menu. Remember the trail map that I mentioned in the previous lecture? Well, here it is, Cloud Native Trail Map. Here's the nice diagram. You can get more information. You can send that to friends, colleagues. And here's a link to the landscape diagram. Here it is. It's super huge. Let's click here on Kubernetes. And here you get very interesting information. Well, you get the repository where the project is stored. You get the number of stars and the activity number of commits here. You get the website address and also the Twitter handle here. So you should follow the Twitter feed of the project that you are using. So let's close this one. Let's click here on Helm. Again, website, repository, number of stars, activity, and the Twitter handle. And this concludes this look at the CNCF website. Let's now talk about the containers concepts. Containers, containers, containers. They are everywhere, but what are they exactly? A container is a unit of deployment. It contains everything needed for the code to run. So the compiled code, the runtime, system libraries, and the system tools. You take a container, push it on a server, and it should run. Of course, it can have some external dependencies like a database or a cache, but the code deployed in it should run as is. So why use containers? Because it is faster to deploy something small than something big, like a complete monolithic system. They use fewer resources. They are smaller. And since they are smaller, you can fit more on the same server. When using CI/CD techniques, they are a lot faster to deploy. You can run them anywhere. And they are isolated from each other, meaning that if one fails, it will not take the whole system down with it. So what exactly is virtualize? Let's compare virtual machines with containers. A VM runs on some kind of hardware where an OS is installed. The OS hypervisor will let you create a virtual machine where you will install an OS. So basically, the VM virtualizes the hardware. And what's happening when a VM starts? Well, you see the BIOS coming up, and then the OS boots up. And what about the size of that VM? Let's say we have a Windows Server VM. It can take 12 gigabytes of RAM and 500 gigabytes of hard drive space. And how long does it take to boot? Well, depending on multiple factors, something like 5 to 10 minutes. Now, let's compare that to containers. We still have the hardware and the OS, of course. There's a container runtime installed in the OS, and containers images are run in memory. Now, compared to a VM, a container does not have to boot because it will use the host OS kernel. This means that container starts in seconds because they don't have to boot. They also use a lot less memory and hard drive space since there's no OS. A small container can take 100 megabyte of hard drive space and run in 64 or 100 megabyte of RAM. So, VM and containers. Virtual machines have a larger footprint, they are slower to boot, ideal for long-running tasks. Containers are lightweight, they're quick to start, they don't have to boot, they're portable, and they're ideal for short-lived tasks because you can spin one super fast. So, are containers replacing virtual machines? Are virtual machines obsolete? Absolutely no. Containers are just another tool in your toolbox, and you need to find the right use case for them, and also for VMs. If you're old enough, you must remember what a telephone boot is. If not, well, before cell phones, we used to make phone calls in these booths by dropping a dime or a quarter. Anyways, using a telephone boot analogy, you can pack more containers on the same server than what's possible with virtual machines. Containers are made of layers. You start with the base OS, add customizations, and add your applications. Let's take a deeper look at this screenshot. The Docker pull command retrieves and downloads a container image. As you can see, each layer is downloaded individually. Notice that each has a unique ID, and that for the first ones, Docker says that they already exist. Why is so? Docker uses a local cache to store the container's images, and if a layer already exists, it will not be downloaded again. The benefit is that if you pull version 2 of an image, Docker will only download the layers not present in its cache. One of the goals when creating container images is to create them with the smallest number of layers possible. Later on, we'll see techniques on how to achieve that. Now, can you write on these layers? Well, no, except for the top one, because it is read-write. The lower ones are read-only. Another concept is the container registry. It's a centralized repository where you deploy the container images you create. Think GitHub, but for containers. Docker has one called Docker Hub that provides public and private repositories. And all major cloud providers have container registry services. The last container concept is the orchestrator. An orchestrator allows us to manage, scale, monitor the containers that we run on our servers. You can install your own or use a managed cluster offered by one of the cloud providers like AWS, Azure, Google Cloud. We will come back to the orchestrator concepts after we have a better knowledge of containers. And this concludes this lecture on the containers concepts. Let's now understand what is Docker. So, what is Docker? That may seem like a simple question, but there's more to it. There's Docker the company and Docker the platform. Docker maintains the Moby project, an open source container runtime that follows the specs from the Open Container Initiative. Docker sold its Docker Enterprise Division late 2019 to a company called Kubernetes. So if you want to buy enterprise support or get certified with Docker, you have to go through Kubernetes. Docker provides a container runtime that runs on Mac, Windows, and Linux, a command line tool to create and manage containers, a Docker file format for building containers, and interestingly, Windows lets you create both Windows and Linux containers. A quick tip. If for some reason Docker doesn't seem to work on your machine, try restarting it by using the Restart menu from the system icon on Windows, or by clicking on the debug icon in Docker Desktop on Mac and Windows, and clicking on Restart. Docker Desktop is very stable, but I had some issues when my laptop was coming back from hibernation, but that was a long time ago, and I haven't had issues for a while. And this concludes this lecture on Docker. The easiest way to run Docker on your machine is by running Docker Desktop. It's a free download available on docker.com. So you click here on Get Started, and you download the version for your OS. So Windows, Mac, Linux here. Now, if you're running Windows, check the version of Windows that you're running. If you're running Windows 10 version 2004 or a later version, you can run what's called Windows Subsystem for Linux version 2. So WSL2. Basically, it allows you to run a Linux distribution right into your Windows installation. So Docker Desktop can run its container by installing a virtual machine inside Hyper-V. Or if you have WSL2 installed, it will install that virtual machine inside the Linux distribution, and everything will be a lot faster. So that's the preferred way. So just to prove a point here, I'm going to launch my Hyper-V manager. And as you can see, I'm not running any virtual machine. So my Docker Desktop installation uses WSL2. You'll find a link to this installation guide in the modules notes. Okay, so let's take a look at the Docker Desktop. I'm running Windows. As you can see, I can see my Docker Desktop system tray icon here. So for Mac user, it will be at the top of the screen, of course. I can right click on it and let's select Dashboard. All right. So here I can see a list of containers that are currently running. I can stop them, restart them, delete them. I can see a list of images that are installed on my machine here. We'll come back to that later on. There's a gear icon here. That's the setting icon. And in the general section here, you can see that WSL2 is enabled. So that's why Docker Desktop doesn't use an Hyper-V virtual machine. It uses the WSL2 to run the VM. And there's the Kubernetes menu here. If I select it, I can see that Kubernetes is enabled. So when you check that, Docker Desktop will download additional containers to run Kubernetes right onto Docker Desktop here. So very useful. There's a bug icon here, which is the troubleshoot icon here. So if at some point you're issuing Docker commands and they don't work or something's wrong running Docker commands, you can click here on the restart button here. You can see my name here. It means that I'm currently logged. And if I right click down on the system tray icon, you can see that I'm currently logged in and I have the option to sign out. So what username and password did I use to log in? When you downloaded the Docker Desktop, you could have created a Docker account or a Docker Hub account. So that's the same username and password. So if you go to hub.docker.com and you logged in, well, that's the same account that is used here in Docker Desktop. Let's take a look at your first Docker CLI commands. Now, throughout this course, I will introduce you to various commands. I will list them in what I call a cheat sheet list, like what you find on this slide. I will briefly explain what the commands are for, and that will be followed by a concrete hands-on demonstration. So when you install Docker Desktop on your Mac or PC, it also installs the Docker CLI tool. Our first command is docker info. This will display some information about the Docker installation on your machine. Docker version will display its version. And Docker login will log you into a Docker registry. By default, this login command will log you into Docker Hub, the registry from Docker. And this concludes this lecture on the Docker CLI. All right, we need to open a new terminal window into Visual Studio Code. So let's select a terminal, new terminal, or you can use the shortcut Control-Shift-Backtick key. All right, this will open a terminal window. And let's take a look at the commands that we will run. They're really basic. It's just for testing that our Docker installation is working correctly. So let's type docker info. This will give me some information about my current installation, what's happening. I have 47 containers, 3 stop, 44 running, 25 images, and so on and so on. So information that is quite useful for debugging purposes. I can see that the virtual machine running Docker Desktop is running has 2 CPU. It has 2 gigabytes of memory allocated. All right, sounds good. Let's type now Docker version. And this will give me some information about the version number of different parts of Docker Desktop. So again, useful for debugging purposes. These are not commands that you will run on a day-to-day basis, but they're quite useful for troubleshooting. The last command is docker login. So I'm just going to type docker login without any username password, see what's happening. And well, the command says that I log in successfully. Why so? Well, if I right click here on my Docker Desktop, I can see that I'm already logged in. So that's why I didn't have to input or type any username password. I was already logged in. Let's now see how to run containers. The docker pull command lets you download an image from a registry. Docker run will execute an image in memory as a container. If the image is not present in the Docker local cache, it will be downloaded automatically. Using run with the -d flag will run the container in the background, giving you your command prompt or terminal back. The start command will run a container in the stopped state. Docker ps will list all the containers currently running and add the -a flag to also list all the stopped ones. Docker stop will stop a container running, but the container will still be in memory. We will see how to remove them from memory in a few minutes. Docker kill will, kill a container that might be stuck in memory. You usually don't use this command, but it's useful to know. Docker image inspect will give you some information about an image, very useful for debugging purposes. So you may notice that we have two parameters here. One is called image name and the second one container name. So what's the difference? The image name is the name of the image as you find it in the container registry, and the container name is the name of the running container. So you run an image using its name and then interact with it using the running instance name. The run command has an optional flag called --name that lets you specify a name. If you don't specify one, Docker will auto-generate one for you. You can set limits on the memory and the CPU that the container can use when using the run command. So how do you run a container? Using the docker run command, you specify the image name as found in the container registry. You specify a name for the running instance. And with the publish flag, you map a port from your local host to the port that the container is listening to. You can list the running containers using Docker ps. Notice how we stop the container by using the running name and not by using the image name. Then we remove it from memory using the remove or rm command. Containers are not black boxes. You can attach a shell to your terminal and run commands that will execute right inside the running container by using the -it switch and the name of the program you want to run. Running a Windows container? Well, you can run PowerShell. Using the docker container exec command, you can attach to a running container. Here's a screenshot showing the docker run command. And notice the terminal prompt changing when attached to a container. So how do we clean up things? The remove command lets you remove a container from memory. But first, it must be in the stop state for the command to work. Here's the remove command getting a list of the stopped container and removing them all. The images that you pull will be cached locally. You can get a list of these images using the docker images command. Use the remove image or RMI command to delete an image from your machine. After a while, you may end up with a bunch of images. To do some spring cleanup, use the system prune command. This will delete all the image currently not in use, so be careful using this command. And this concludes this lecture on the Docker CLI. Let's now run our first container. We'll run an Nginx web server, so something pretty basic. That'll be perfect for this lab. All right, let's open a terminal. So terminal, new terminal, or Control-Shift backtick. Perfect. So we'll run this command. So let's take a look at the command first. So we'll run a Docker run, and let's go at the end of the command. This will be the image that we'll run. So an Nginx image. We'll give it a name. So the name will be web server. That will be the name of the running instance. We'll map local host port 8080 to the port that the container is listening to. So port 80. And -D for detached mode, so we can get our command prompt or terminal prompt back. So let's run this. Something interesting is happening. Unable to find image Nginx latest, and you see that Docker has pulled all the different layers locally here. So now, if I issue a Docker PS, it will list the containers that are currently running. So I have 3 containers running. So the Kubernetes dashboard and the metric server here. So don't look at these. Let's focus on this one. So this is the containers that we just launched, the Nginx image here. It started 30 seconds ago. We can see that port 8080 localhost is mapped to the port 80 here, and the name is web server. So let's launch a web browser, and let's type localhost 8080. The container is actually running. Fantastic. All right. So we can get a list of the images installed on your machine here by using Docker images. So I have a bunch. I may have a lot more than you, but let's focus on the last one here. Nginx, the tag is latest, image ID, and this is the size. All right, fantastic. Let's try to connect to it. So we'll issue a Docker container exec. We'll give it the name, so the running instance, and the program we want to run. So look at the prompt now. Root at some ID. So the ID is the actual container ID. So I'm logged in as root on that container. So now I can issue some commands. So let's do an ls. Let's type ls bin to see what's in there. So different commands. So I'm connected to that running container. That's pretty cool. So I can issue commands, look at the logs, if any, and do some troubleshooting. So this is super useful for debugging purposes. We'll use that a lot in the various steps that we'll do together. All right, let's get out of there by typing exit. All right, just clear my screen here. So our container is running. How do we stop it? We use the Docker stop command, but look at the parameter that we use, the name of the container that we use. We use the running instance name, not the name of the image. So that's pretty important here. Docker stop web server. All right, but the container is still in memory. If I do a Docker PS, it's not listed anymore as a running container, but if I type Docker PS dash A. Aha, for all, I can see that my container is still in memory here. So I need to remove it from memory. So we'll use the docker rm and the name of the running instance. So rm for remove. And now the container is no longer in memory. Awesome. Now, the container is still, well, the image that was used to create the container is still on my machine. So if I type docker images, you see it's still here. So that takes 133 megabyte of disk space. If I want to get rid of that, I use the RMI, so remove image command, and the name this time of the image, not the name of the running instance, because none are running right now. And you see all the layers have been deleted. Let's now see how we can build containers. Docker build lets you create an image using a Docker file. If you run the command in the same folder where the Docker file is located, simply use a dot as the file name. If the file is located in a different folder, specify the location using the F flag. The tag command lets you assign a name to an image. This tagging has two parts, a name and a tag. The tag is usually used to specify the version number. So, what is a Docker file? Well, it's a text file listing the steps to build an image. Here's the simplest Docker file I can imagine. 2 lines. The from command specifies the base image. When building new images, you always start from something already existing. In this case, an image with the Nginx web server using the Alpine version. And then the copy command copies everything from the current folder to a folder inside the container. Using the build command, we create a new image specifying the Docker file. Remember to use the dot when the file is located in the same folder. Here's another one, this time a little bit more complex. It is used to create an image running a Node.js app. Let's take a look at it. The from command specifies the base image. Using the run command, we run the package manager inside the container to install Node.js. Next, we copy all the local files into a folder named src inside the container. We use the run command to do an npm install. We then add some metadata. In this case, we tell the container to listen on port 8080. And finally, we tell the container what to run when starting. So, as you see, this Docker file contains the steps needed to run our Node.js app. We saw what tagging was a moment ago. Let's explore this again. Using the docker tag command, we name an image using a name and optionally a tag. If you don't specify a repository name, it will default to Docker Hub. Later on, we'll see how to push images to different repositories, and we'll have to specify the repository name when tagging our images. And this concludes this lecture on how to create Docker images. Let's see how can Visual Studio Code help us build and run containers. So what is Visual Studio Code and why talk about this tool in this course? Well, it's a text and code editor. It's free and open source. It runs on Windows, Mac, and Linux. And you can download it for free using this link. So you will work a lot with text files, creating Docker files, and later on Docker Compose and YAML files. A tool like VS Code will help you because you can install plugins that will make your life easier. Using a different text editor? No problem. In VS Code, you can install plugins by clicking on the extension icon in the left menu. Then you search for Docker and install the extension from Microsoft. The extension lets you add Docker files to your projects using the command palette. Open it using the View menu or type Ctrl-Shift-P. Type Docker add and select Add Docker files to Workspace. The extension will ask you a few questions and will create the Docker files for you. VS Code has a built-in terminal where you can type commands, or you can run commands using the command palette. Here's another example when running a container. And when using the command palette, there's no magic there. The extension will simply issue a command in the terminal. But sometimes it's a great way to learn. Creating Docker files is okay, but what I like the most is the UI provided by the extension, helping me manage my container. So if you click on the Docker icon, you can see the images installed on your computer. And you can even see the containers currently running. Right-click on an image to manage it. Same thing for the containers currently running. Very, very, very useful. And this concludes this lecture on VS Code. Let's now use Visual Studio Code to containerize a Node.js Express application. So I already installed the Docker extension in Visual Studio Code, but let's take a look at it. So if I click here on extensions, and let's search for Docker, here it is. That's the one from Microsoft, almost 6 million install at the time of recording. So that's the one. All right, so let's go back to our files. So I have my Node.js application here. If I click here on package.json, the name of my application is my Express app. So that'll be important in a few seconds. All right, so let's first add the Docker file to our project. So we'll use the tooling provided by the extension to do that. We'll go to the View menu, Command Palette, or you can use the shortcut, Ctrl-Shift-P, right? And we'll type Docker add. And there are two options here, Docker files or Docker Compose files. So we haven't looked at the Docker Compose file, so let's select the first one, Docker files. The extension hack is asking us about the application platform. So it's a Node.js application, but it can generate Docker files for .NET, Python, Java, C++, Go, and Ruby apps. So let's select Node.js. All right. And next it's asking us where is the package.json file. So here it is. It's at the root of my application. So I'll select this one. The port that the application is listening to, 3000, perfect. And do I need the optional Docker compose file? No, not at this time. All right, so the extension quickly added the Docker file and also a Docker ignore file and also a folder for VS Code. So let's take a look at the Docker ignore. Basically, it's a list of files not to deploy in our container. And the Docker file has been created for me. It uses a node base image. It copies everything into the container, the image, and expose port 3000. Perfect. So let's now build this image. So we'll go back to the command palette, view command palette, Control Shift P, and this time we'll search for Docker build. All right, here it is. Docker images, build image. All right, so I just issue the command and look at what's happening. The extension is not a black box issuing some crazy or strange commands in the background. It's just issuing a Docker build command here. And remember, a few seconds ago, I mentioned that the name of the application in the package.json file is important. Well, that's the name of our application here. So the extension use it to generate the name for my image. All right, it's just a Docker build command, nothing fancy, but using this extension is a great way to learn about some commands that you may want to use at a later time from the terminal prompt. Okay, terminal will be reused by task. Press any key to close it. Let's press any key. All right. The image has been built. Let's run it now. So view, command palette. Okay, Docker run. So we'll use the first one. And there's a list of my images. And here is my Express app. Perfect. Let's run that. Select image. That's the tag latest. Perfect. And look at what's happening. Docker run -d-p for the localhost port 3000 to the port that the container is listening to. So nothing fancy here. It's commands that you can type yourself, but the extension do that for you. So if I start my browser, localhost, and I go to port 3000, there it is. So that worked. Perfect. Let's now close this. Let's now use the UI provided by the extension. So in the left menu, let's click on the Docker icon here. And from there, you have a list of the running containers, the images, and the different registries that you connected to. All right. So here's our Express app, my Express app, latest, and its running name, the instance name is called magical_direct. Why so? Well, when we issued a Docker run command using the command palette, the extension didn't provide a name, so one was generated automatically by Docker. So from there, I can view the logs, attach shell, inspect, open in a browser. So if I select that, there it is. That's my app, listening on port 3000. I can stop it, restart it, remove it. So let's remove it here. So are you sure you want to remove container? Yes. It's not in memory anymore. It's not running anymore. But if I look at the list of the images that I have, Here it is, my Express app. So I can right click on it and I have a few options. I can run it, inspect it, pull, push, tag, and even delete it. So let's run it. Okay, and you see at the top, my Express app, and look at the name, gifted underscore El Bakian. Because if you inspect the Docker command that was issued by the extension, there's no name provided. So Docker generated one for us. All right, so let's close this. We can stop or remove it from memory. And if we no longer need the image, we can just remove it here. Are you sure you want to remove the image? Blah, 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 blah. Okay, let's remove it. And it's gone. So what's happening in the background is that the extension is simply issuing a Docker remove image, RMI, to remove the image from this. So nothing really fancy. The extension is not a black box that is issuing some strange commands. It's just regular Docker commands. But I really like the UI provided here. And so instead of typing, okay, let's try this. Let's clear this and let's type Docker images. Here's a list of all my images, but here I have a nice UI listing all the same images here. So sometimes it's easier having a little UI to help you accomplish some task. Other times it's easier issuing the commands from the terminal or the command prompt. So it's up to you. You can use the UI or the terminal. Let's talk about data persistence. Containers are ephemeral and stateless, so you don't usually store data in them. Of course, you can write data in a container, but if you destroy one or if it crashes, any data stored in it will be lost. So it's okay to write some log files or scrap data that you don't want to keep, as long as you understand that you will lose these files at some point in time. To persist data, you need to store it outside the container in what we call a volume. A volume maps an external folder or even a cloud storage service to a local folder inside your container. So your app sees a volume just like any regular folder. The O's in this diagram represent the server or the virtual machine where the container is running. As you can see, a local folder is mapped to the VM file system, so data stored in a volume will survive a container restart or crash. There's still a chance that we can lose the data if the VM crashes. So later on, we'll see how we can use some type of external storage provided by the cloud provider. But first thing first, in the next lecture, you'll see how to create a volume that maps to a VM file system. And this concludes this lecture on data persistence. Let's see how to create volumes. Here's a cheat sheet listing the Docker commands for managing volumes. Docker create volume will create a new volume. Volume ls will list all the volumes. Volume inspect will get you information about a volume. Volume remove will delete a volume, destroying all the files stored in it. And volume prune will delete all the volumes currently not mounted or not in use. So be super careful using this command. All right. You first need to create a volume using the docker volume create command. Then, when you run a container, you need to use the vSwitch, or the volume parameter, specifying the volume name, a colon, and the name of a local folder. That folder will be a logical folder in your code. So your code will see it just like any regular folder. If you use the inspect command, you'll see the logical folder location in the VM. Instead of using a volume, you can specify a local folder. This is great for testing purposes. Let's say you started developing a service and that you want to test on your dev machine if your code can read and write some files correctly. You can use this kind of mapping, but don't use that in production. Using the inspect command, you can see the local folder path. And this concludes this lecture on volumes. Let's now persist some data outside of a running container. So to do that, we'll use a volume. So I'll open a terminal and we'll use the docker volume create and the name of the volume. So this will create a volume. Perfect. Let's now list the volumes on my machine. So there's a few here. The first 4 were created earlier. This is the volume that we just created. Now let's run an Nginx image and let's attach or map a local folder to that volume. So we'll use docker run -d for detach. We'll name our instance vol-test. With the -d for volume, we'll use the volume name that we created earlier and map that to a folder called app on our Nginx image. All right, let's do that. Okay, excellent. So that worked. Now let's connect to our running instance. So docker exec -it, the name of the instance, and we'll run bash here. Perfect. Let's first do an ls to see if we see the app folder. There it is. So that folder is mapped to the volume. So anything that we store or write in that folder will be written externally outside of the container. So that will persist. All right. Just for fun, instead of doing a cat, let's install nano inside the running instance. So I'll do first an apt-get update. Remember, this is running inside the container, and we'll install nano apt-get install nano, which is a small editor. Perfect. I'll cd into the app folder and open nano. So nano, and we'll create a file called test.txt. Hello volume. All right. And we'll use Control O to write to disk. Control O, enter, and Control X to exit nano. Perfect. If I do an ls here, I should see my file. There it is, test.txt. So let's exit the running instance. And what we'll do, we'll stop the running instance and we'll remove it from memory. Stop it here. And we will remove it from memory with rm. Okay, so now the container or the instance is gone. If we would have stored some data inside that container, it would be lost at this point. But we use a volume, so the data was stored externally. So let's try to create a second instance. Same thing, using the same volume, and let's exec to it. Perfect. Let's see what is in the app folder. Here is our file. So let's do cat test.txt just to prove hello volume. That worked. Let's exit here. This proved that by using a volume, your data persists, a container restart or crash here. The data is still there until I remove the volume. So if I issue a Docker volume remove and the name of the volume, you see, doesn't work. Why? The error says that the volume is in use. Interesting. So I need to stop any container instance that is running and remove it from memory before deleting or removing a volume. Let's try again. Docker volume rm for remove my volume, and this time it worked. Now, another thing I want to show you, let me create it again. Perfect. And let's switch to the Docker UI here. If I click Docker here, there's a section that lists the different volumes here. So my vol is listed here. So here I can inspect. I cannot look at the files, but I can manage it. So I can click here on remove. That will delete the volume. Are you sure? Yes. Let's now see the YAML concepts. YAML stands for YAML Ain't Markup Language. It's a way to serialize data so that it's readable by human beings. It's the file format used by Docker Compose and Kubernetes. Here's a sample YAML file. For a key value pair, you specify the key, a colon, then a space, and the value. Don't forget the space, it's mandatory. Here are some nested values. You specify child values using two-space indentation. And quotes are not needed for string values. Here's a list. Again, the child elements are indented with two spaces, and there's a space after the dash. This is what we call the block style. There's also a flow style that looks like JSON. So you may be tempted to use it if you're familiar with JSON, but don't. I never saw any sample or any documentation using this flow style. Since it's easy to forget a space, and you can spend quite some time figuring out why your YAML file doesn't work, you can use tools like this linter available on yamllint.com. It will parse your YAML and flag any errors. Very useful. And this concludes this lecture on the YAML concepts. Let's now take a look at the Docker Compose concepts. Let's say that your app is composed of multiple containers. You run the front-end container using a docker run command, docker run again for the backend container, and again for the Redis cache container. So you end up issuing multiple Docker run commands to run your app. Would it be nice if you could deploy your app using one single command? Well, that's the Docker Compose goal, to define and run multi-containers application using a single YAML file. There's a Compose plugin that extends the Docker CLI and lets you run those Docker Compose files. The specifications are available here. If you looked at Docker Compose before, you may have seen that sometimes the commands are using an hyphen, so docker-compose, and sometimes they do not. Why is this? At the DockerCon conference in 2022, Docker announced the general availability of Compose version 2. Okay, this means that there was a V1 before, and the V1 command line tool was installed separately from the Docker CLI. It was built using Python, so you needed to have Python installed to run Compose V1, and the syntax was docker-compose. Compose V2 is a drop-in replacement, meaning that all the V1 commands are working as expected. It's installed as a Docker CLI plugin automatically by Docker Desktop. To use it, you type docker space compose. No hyphen needed here. It's written in Go, so no need to have Python installed to run the command. In summary, it's simply a faster version of the Docker Compose tool shipped as a Docker plugin instead of a Python application. Here's a Docker Compose file. There are 3 containers defined in it: Web API 1, Web API 2, and API Gateway. The name that you use here defines the network or host name for that container. The code running inside your container can use these host names to communicate between each container. For each of them, you specify the image to run. You set the internal and external port the container will listen on. Note that the API version is now optional, so it's okay to skip it. You may ask yourself, should I use Docker Compose or not? Docker Compose is perfect for small workloads that don't require a full orchestrator like Kubernetes. It's perfect when developing and testing locally before deploying to Kubernetes. Some cloud providers offer services that support Docker Compose, like App Service on Azure and ECS on AWS. And of course, you can simply use a virtual machine or a VPS, virtual private server, with DigitalOcean or Linux. And this concludes this lecture on the Docker Compose concepts. Let's now use Docker Compose. Here's a cheat sheet listing some of the Docker Compose commands. Docker Compose build lets you build the containers as defined in your Docker Compose YAML file. If the file is located in another folder, you can use the optional -f parameter and specify the file's location. Start will start all the containers as defined in your YAML file. Stop will stop them, but they'll remain in memory. Up will do a build followed by a start. This is super handy. Use the -d parameter to run the command in the background and take back your terminal prompt. PS will list what's running. Remove or RM will remove the containers currently from memory. Down will do a stop followed by a remove. Again, this is super handy. Logs will display the logs for a container. And you can open a session inside a container by running docker compose exec, the container name, and the program to run. The Docker Compose file is located inside a folder. And if you run Docker Compose up, this will launch your application. If you try to run Docker Compose up a second time from the same folder, nothing will happen because the application is currently running. If you want to run a second instance of your application, it was impossible with Docker Compose v1. But with v2, you can use a project name to launch a second instance of your application from the same folder. Here's a cheat sheet for some of the new commands. Docker compose -- project -name followed by a project name. This will run an instance of the application as a project. The shortcut is much shorter to type. -p instead of -- project -name. You can list the project currently running by using compose ls. CP will allow you to copy files from the containers. So this is super handy to retrieve, let's say, log files. And you can copy files to the container. So from your machine, your desktop or laptop, to the container by using docker compose cp, the source path, the container ID, and the destination path. Here's an example. Imagine that the Docker Compose file is located in the same folder where you run these commands. You simply use the up command to build and run the containers. And to take them down, simply use the down command. And this concludes this lecture on Docker Compose. In this lab, we will deploy a Docker Compose application. Let's take a look at our Docker Compose.yaml file. We have one section called Services, and under that section, we define two services. The first one is called web-fe, fe for front end. It's a Python application, and instead of using an image from Docker Hub, we'll be building that image using the build parameter. The dot means that the Docker file is at the same level as the Docker Compose file. So here it is. It's a simple Python application, just one file, app.py, and requirement.txt that we're copying on that base image. It will be listening on port 5000, and this is our second service. It's a Redis cache, and this time we'll be using an image from Docker Hub. All right, let's open a terminal. And let's build the image using Docker Compose build. Perfect, my image was built. Now I can launch the application using Docker Compose up and -d for detach. Now I could have skipped the build step because up does a build first and then a start. So it's super handy. So let's use Docker Compose up, and my application is up and running. I can test it. If I go to localhost 5000, you visited me one time. I'll do a few refreshes. 5 times, perfect. Okay, I can list the running containers using Docker Compose PS. I can also use Docker PS since it will list the Docker container currently running. And I can look at the logs for my front-end service using Docker Compose logs -f and the name of the service. And if I move that a little bit and hit F5 a few times, you see, new entries are logged. Perfect. That works. Let's do a Control-C to terminate the log streaming. And we'll use Docker Compose ls to list the currently running projects. I have one project running. It's called L09-04 Docker Compose. Well, basically, when I use Docker Compose up, I didn't specify a project name. So Docker Compose used the folder name as the project name. Now let's try to create a second instance of our application. If we use Docker Compose up-d again, well, Docker Compose tell me that the application is running, so it will not start a new version. We can try to deploy our second version using a project name. So Docker Compose -p for project name. We'll name it test up-d. Let's see what will happen. Starting. Oops, we have an error here. Bind for localhost 5000 failed. Port is already allocated. Of course, my localhost port 5000 is in use right now. So what I need to do, I need to change that port here, the localhost port. I'll use 5001. Save the file and use the same command, Docker Compose -p project name test up-d. And this time it worked. Awesome. Let's open our browser and let's go to port 5001. Yes, that worked. A few refreshes, 10 times. Let's go back to port 5000, the first instance, 15 times. All right. So let's do a Docker Compose ls again to list our projects. Now we have two projects. The first one that we deploy without specifying a project name, and the second one with the project name test. Let's delete our first instance by using Docker Compose down. So I didn't specify a project name. Docker Compose used the folder name as the project name. Now, if I do the Docker Compose ls, I should have only one project running. Yes, it's test. Now I can delete that one using Docker Compose, specifying the project name, and down. Let's list the projects again. Docker Compose ls. Nothing running. PS. Listing the containers. Nothing. And why not try Docker PS? Nothing in memory. In this lab, we will deploy a Docker Compose sample application that is composed of 3 services: a web front-end built with React, a Node.js backend, and a MariaDB database. Let's take a look at our Docker Compose file. This is more complex than what we saw so far, so let's try to break it into smaller pieces. Here we have the definition of our 3 services. If we start from the left, we have the backend service. Top right, the database, DB, and the front end. Now, if you look at the DB service, you can see that we're referencing an image that will pull from Docker Hub. And the other 2 services, we're using the build parameter. This means that we will build these two images. Looking at the backend service, we can see that we specify build and context. Context with the value of backend. Backend is actually a subfolder where the Docker file is located. Next, we're defining two networks, public and private. We can see that our front-end service is using the public network. The back-end service is using public and private. And the database service, the DB service, use only the private network. Front-end being in the public network cannot communicate directly with the DB service. But backend, being in both public and private, can communicate with both DB and front-end services. We're defining also two named volumes, backend-modules and db-data. And we can see highlighted in yellow that our DB service is using DB data and our backend service is using backend modules. Highlighted in yellow, we also see that we're using other volumes. These volumes are scoped at the service level and are not shared between services. To create an instance of our Docker Compose application, we simply use Docker Compose up, and to bring it down, Docker Compose down. In Visual Studio Code, let's take a look at the Docker Compose file. So it's called compose.yaml. Here we have our services section, network section, where we define two networks, the name volumes, backend modules and DB data, and secrets that we haven't seen yet, where we're defining one key value pair. So the key is DB password, and we get the secret from a file. The file is located in the folder called DB, and it gets the value from a file called password.txt. If we open the DB folder, here's the file with the value, the secret. And that will be injected when we run Docker Compose up. Okay, let's go back to the services section. And here we have our backend, DB, and front-end services. Let's take a look at backend. We're using the build directive and we are setting the context to backend. It points to this folder called backend here, and the Docker file is located inside that backend folder with the application. Same thing with the front-end service, build, context front-end, and we're getting the Docker file and the application from the front-end folder. And what about the DB service? Well, we're using an image that will pull from Docker Hub. Okay, let's build our two images. We'll open a terminal and run Docker Compose build. Our images were built. Perfect. Now let's run the application by using Docker Compose up-d. Perfect. The application is listening on port 3000. So let's open a browser and type localhost 3000. Here's our React application. It's working. Awesome. We can list the containers that are currently running by using Docker Compose PS. We should have 3. Backend, DB, frontend. Awesome. Let's take a look at the logs from the backend service, Docker Compose logs-f backend. And these are the logs for our backend service. Awesome. We can type Control-C to stop the log streaming. And we can take our application down by using Docker Compose down. This will stop and remove the containers from memory. Do we have something else in memory? We should not. Perfect. Even if I type Docker PS, there's nothing. However, the volumes are still there. When you do a Docker Compose down, it will remove the containers from memory, but will not remove the volumes. So if I open the Docker desktop application and I click on volumes here, I can see that I have three volumes that were created a few minutes ago. So I need to delete them manually. I can select them right here and click on delete, or I can do the same thing by clicking on the Docker icon in VS Code, locating the volumes here and delete them. Find it easier to do that in Docker Desktop because we see when the volumes were created. So I'm pretty sure that these three are the ones that I need to delete. I'll click on the delete button and confirm. Let's take a look at some of the Compose file features. It's a good practice to set limits on the resources that your container will use. In this example, highlighted in yellow, we tell Docker to start the container with 1/4 of a CPU and 20 megabytes of RAM. The green section is the limits that we are allowing. In this case, half of a CPU and 150 megabytes of RAM. To set an environment variable that will be injected in the running instance, simply set the key value pair in the environment section. Those values can be overridden at the command line using the -e parameter. You can reference an environment variable using the $curly bracket syntax. This way, you can set the variable on your machine or server and use it directly in the compose file. You can place the values in a file that you'll name .env, located in the same folder as the compose file. The compose command will automatically read the values from that file. By default, all containers specified in a compose file will see each other using their service names. Here, we have two services, web and DB. The code running in the web service can communicate with the second one using DB as the host name, and vice versa. The web container is visible from outside of the Docker network using the port number configured in the left portion of the port's value. Web is listening inside the Docker network on port 80. DB can reach web on port 80. Finally, DB only exposes one port number. That's the internal port. Web can reach DB using port 5432, but DB is not visible from outside the Docker network. If you have a Compose application with multiple containers, you can restrict who sees who by configuring networks. In this example, we're defining two networks, front-end and back-end. Proxy can see app because both are part of the front-end network. However, proxy does not see DB because it's not part of the backend network. When using multiple containers, you may want to start some of them first and wait until they are running before starting the other ones. A typical use case is a database that you want to run before starting the main application. Doing so is easy using the depends on parameter, where you simply specify what is the service name that the service is dependent on. In this example, app depends on DB, so Compose will first start DB, and when DB is running, Compose will then start app. You can declare volumes in the volumes section. These are called named volumes, and they can be used by all these services that you are declaring in the Compose file. To use a volume from a service, map it to a local folder using the volume name, colon, and the virtual path inside the container. Optionally, you can make the mapping read-only by appending colon RO to the mapping. You can also create a mapping without using a named volume. This mapping can't be shared across services. It's also a good practice to set a restart policy. Let's say that you deploy your Compose app in a VM, and at some point, you need to install some OS patches, and you need to restart or reboot the server. What will happen to your Compose app? Well, if you don't specify a restart policy, the one by default is no, meaning that Compose will not restart the containers if they were shut down by reboot. You can set the policy to always. This way, Compose restarts the containers until their removal. On failure, restarts a container if the exec code indicates an error. And lastly, unless stop does a restart unless you stopped or removed the containers. And this concludes this look at some of the Docker Compose features. Let's now talk about container registries. So, what is a container registry? It's a central repository for container images. You build an image locally, then you push and store the binary, the different layers, to the repository. They can be private or public. The default one is Docker Hub. Microsoft, AWS, and Google each offer container registries as a service. The benefit of using a repository from your cloud provider is that the images are located near your app, so no hops over the internet to retrieve the images. So let's say we want to retrieve an image from Docker Hub. We issue a Docker pull command, and Docker downloads the images layers and store them in its local cache. And this concludes this lecture on container registries. Let's see how to push and pull images to Docker Hub. Make sure you are logged in with your Docker user account. To be sure, simply type Docker login without a username and password. Docker will tell you that you're already logged in. If not, enter your Docker username and password. You need to tag an image with the repository name. By default, it's your username. If you have created some organization in Docker Hub, prefix it to the name of the image. In this example, I want to push this image to my Kate's Academy organization. Then, use the push command And don't forget to specify the organization name. It's part of the image name. To retrieve the image, we use the pull command with the image full name. On Docker Hub, public images are available for download to anyone. If you don't want to share them, you need to create a private repository. Later on, we will create one using our cloud provider. And this concludes this lecture on Docker Hub. Let's now push our first image to Docker Hub. First thing first, let's make sure that we can log in into Docker Hub. So if you head to hub.docker.com, make sure you can log in. Also, if I right click here on my Docker desktop icon, I can see that I'm logged in. Perfect. We will containerize a Node.js Express application. So we'll first add the Docker file. We'll use the tooling. So view, command palette. You can type Docker add and Docker files to workspace. This is a Node.js application. The package.json file is located at the root, so that's the correct one. It's listening on port 3000, and we don't want Docker compose files. Perfect. Now we need to build the image. So let me open a terminal. Perfect. And we need to issue a Docker build command with the -t for tag parameter. But notice here, we need to prefix the name of the image with our registry name. If I select this, I need to prefix that with my name here, the name of my registry. Let me run that. The image was built successfully. Now I need to use the push command to push that image onto Docker Hub. Again, I'll select this and let's replace the registry name with mine. Use your own. And see what's happening here. Docker is pushing each layer to my Docker Hub account here. All right. No errors. Things went fine. Let's go back here. I'm going to refresh this page. And here it is. Here's my image here, my Express image. So I can click on this. I can edit the information. I can see that I have my tag is v1, right? I can get more information here. I can here click on public view. So by default, the repositories on Docker Hub are public. Anyone can download and view and download your images. This is the view for someone who would look at my image. So with the pull command, Docker pull, let me go back here. I can see the tags and so on and so on. And if at some point you want to delete this, you go into the settings tab here. You scroll down and you can delete that repository here. All right, let's go back. Now let's try to pull that image to our computer here. The first thing I will try to do is remove it from my computer. Let me type this, RMI, so remove image. The image has gone completely. So now let's try to pull it from Docker Hub. Okay. Perfect. Pull complete. My image is back here. Now, you see that I use the v1 tag here to tag my image with the version number. So let's try to build a version 2 of that image. Let me copy that. And again, let's replace this part, this placeholder, with my registry name. Image has been built. So let's now push it to Docker Hub. Same thing as we did before, but this time we're pushing version 2. Okay. Let's go back here. Let's go back to my Express or the General tab. Look here, I have V1 and V2. If I click here on tags, I can see when the image was pushed, tags, and people can download V1 or V2. If I want to remove my images, I use the RMI command, so remove image. I'll remove V1, and also I remove V2. And on Docker Hub, if I no longer need this repository, I click here, Settings, scroll down a little bit, click on Delete Repository, and I need to enter the name of my repo just to make sure, and click on Delete. And now it's gone. Time to introduce Kubernetes. So Kubernetes, or also known as K8s, so the letter K, followed by the number 8, so 8 letters, and then the number S, and it's pronounced K8s. So Kubernetes is a project that was created at Google. Version 1 came in July 2015. It was the third generation of container scheduler from Google. Previous projects were Borg and Omega. And Google donated the Kubernetes to the CNCF, so now the development is supervised by the CNCF. It's currently the leading container orchestration tool. It's designed as a loosely coupled collection of components for deploying, managing, and scaling containers. It's vendor neutral, so it's not attached to a single company, and it runs on all cloud providers. And there's a huge community ecosystem around Kubernetes. So what Kubernetes can do? Service discovery, load balancing. It can bridge to the cloud provider's storage services. It can provide rollout and rollbacks capabilities. It can monitor the health of the containers, can manage configuration and secrets. And the same API is available either in a on-premise installation or in every cloud provider. So what can't Kubernetes do? It can deploy or build your code. And it does not provide application-level services like databases, service buses, caches. Here's a quick look at the Kubernetes architecture. This diagram was taken from the Kubernetes documentation. We'll take a closer look at each component, but for now, let's just say that it's composed of a master node, also called the control plane. So that's the portion to the left. And the control plane runs the Kubernetes services and controllers. And you have the worker nodes. These nodes runs the containers that you'll deploy in the cluster. So a container will run in a pod runs in a node, and all the nodes form a cluster. And this concludes this intro to Kubernetes. Let's see how you can run Kubernetes locally. So, do you need to install a Kubernetes cluster in the cloud or ask your IT department to install one in your enterprise so you can test locally? Absolutely not. There are many ways that you can run Kubernetes on a desktop or laptop. Docker Desktop lets you run Kubernetes. Micro-K8s from the makers of Ubuntu and Minikube also let you run Kubernetes. All three requires that virtualization is enabled. Kind runs over Docker Desktop and offer extra functionalities. Docker Desktop is limited to one node, but it's usually not a problem. Micro-K8s, Kind, and Minikube can emulate multiple worker nodes. On Windows, Docker Desktop lets you run both Linux and Windows containers. And you can't create and run Windows containers on Mac and Linux. It runs on Hyper-V or Windows Subsystem for Linux. So if you have Windows 10 version 2004 or later, it's the recommended way to run Docker Desktop. If Hyper-V is enabled on your laptop or desktop, you can't run another hypervisor at the same time. And Minikube used by default VirtualBox, but it can also run on Hyper-V. You can install Docker Desktop on Windows using Hyper-V, and it will create a virtual machine named Docker Desktop VM. When you tick the Enable Kubernetes checkbox in Docker Desktop, it will download additional containers to run Kubernetes. Using Windows 10 version 2004 or later, and if you have WSL2 installed, you can use the WSL2 base engine, and Docker Desktop will create its VM inside the Linux distro you installed on your Windows machine. Note that this is the recommended way to run Docker Desktop. On Mac, Docker Desktop uses the HyperKit lightweight hypervisor to run its VM. Minikube is another popular option. It does not require Docker Desktop. It runs on Linux, Mac, and Windows, and it requires an hypervisor like VirtualBox. Here, we can see Minikube running on a Mac and its virtual machine in VirtualBox. If you need to install Minikube on Windows but don't want to install VirtualBox, you can run Minikube on Hyper-V. You need to create a network switch and start Minikube with some extra parameters. Kind stands for Kubernetes in Docker because it runs on top of Docker Desktop. Kind lets you emulate multiple control planes and multiple worker nodes. This is useful if you need to test node affinity. And this concludes this lecture on how to run Kubernetes locally. This will be a super quick lab just to validate that our Kubernetes installation is working locally. So here I'm on Windows and I'm using Docker Desktop, and I installed Kubernetes with Docker Desktop. In the system tray, I can right click on the Docker Desktop icon. On a Mac, you can do that from the top of the screen. And I will select Dashboard. And from there, I'm going to click here on the gear icon, the settings icon. And I'm using WSL2 to run Docker Desktop, so that's the recommended way. And here, if I click on Kubernetes, enable Kubernetes is checked, so Kubernetes is installed. But is it running correctly? Let's find out. Let me go back here. Let's open a terminal. And let's run this command, kubectl cluster info. That should give us a little information about what's running. So Kubernetes master, it has in green, yay, it's working. So it's running at this address, and kubedns is running at this address. So by running kubectl cluster info, you get some information about the Kubernetes installation and its health. Let's see how you can use the Kubernetes CLI. The Kubernetes API server is a service running on the master node. It exposes a REST API that is the only point of communication for Kubernetes clusters. You define the desired state in YAML files. Let's say you want to run X number of instances of a container in the cluster. Using the Kubernetes CLI, you then send that desired state to the cluster via the REST API. Other applications like a web dashboard can also communicate with the REST API to display the cluster state. kubectl is the Kubernetes CLI, and it runs on Mac, Linux, and Windows. And you pick your choice of pronunciation. kubecontrol, kubectl, kubectl, doesn't matter. It communicates with the API server, and its connection information is stored in a config file under the .kube folder. Let's now see what a context is. It's a group of access parameters that let you connect to a Kubernetes cluster. It contains the cluster name, a user, and a namespace. The current context is the cluster that Kubernetes commands will run against. Let's say that you can connect to 3 clusters, cluster A, cluster B, and cluster C. When you set the default context to cluster B, then all the kubectl commands that you will run against cluster B. Here's a cheat sheet for context commands. kubectl config current context will get you the current context. Get context will list all of them. kubectl config use context and the context name will set the current context. And delete context with the context name will delete the context from the config file. There's a large ecosystem of free open source Kubernetes tools that you can use. kubectx is a good example. It's a shortcut for the kubectl config use context command. You simply type kubectx followed by the context name to quickly switch context. It runs on Windows, Mac, and Linux. Very useful. And this concludes this lecture on the Kubernetes CLI and the concept of context. A context contains connection information to a Kubernetes cluster, and you can have one or more than one context set on your machine. It's super important to know how to figure out in what context you're currently in and how to change context. So first thing first, let's figure out in what context we're currently in. I'm going to use kubectl config current context. And this will print the name of the context we're currently in. I'm currently in the Docker desktop context. Means that whenever I type kubectl commands, they'll be applied to that Kubernetes cluster. All right. I can have more than one context configured on my machine or on any machine or server. To list them, we use kubectl config get dash context. And here we can see that I have two contexts set on my machine. Docker desktop, which is the current context because it has that star in the current column. And I have a second one called demo. Demo is a cluster that I created in the cloud. What if I want to change from Docker desktop to demo? Okay. Let's use kubectl config use dash context and the context name. Demo. And now if I print again the current context, there it is, demo. So whenever I'll be typing kubectl command, these YAML files, this command will be sent to my demo cluster somewhere in the cloud. A cool tool is kubectx because it allows you to, well, instead of using kubectl config, blah, 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 basically it's a shortcut. If I simply type kubectx, that will print the context that I've configured on my machine. So demo is green, means that it's the current context. And I can quickly change context using kubectx and the context name. Docker desktop, a little bit less keystroke to type, but anyway, it's a fun tool. If I want to rename context, let's say your cluster has a long, funky name and you want to rename it to make more sense, you can use the kubectl config rename context, old name, new name. So let's try to rename our demo cluster here. Demo, let's say it's on Azure, so Azure demo. Okay. Let's use kubectx to print the context, and there it is, Azure Demo. Where is that context information stored? It's stored locally on your machine. So I'm on Windows. Let's see where it is. It's on the C drive, users, your username, under .cube, the .cube folder. And there it is, config. So if I right click on it and select open in with code, we can see that it's a YAML file. And it contains two entries here, two clusters. One is the Azure one, and the second one is the Docker desktop one. And this is the different context that I have. So here is my Docker desktop context. And here is my demo context. Well, the cluster name is still demo, but I renamed the context name to Azure-demo. There it is. All right. Let's go back here. And let's say that I've deleted my cluster in the cloud. I don't need it anymore. I want to get rid of the context information. I can use kubectl config delete context and the context name. So let's try this. Azure demo. Deleted context Azure demo from the config file. So let's take a look here. And you see that now I have only one context. And here's the current context in this line here. But let's take a look here at the clusters list. My demo cluster is still there. right? So it's not deleted automatically. What you can do is simply edit that config file and remove the section no longer needed. Let's talk about the declarative and the imperative ways to create resources in Kubernetes. There are two ways that you can use when you want to create resources in Kubernetes: the declarative way and the imperative way. Using the imperative way, you use kubectl to issue a series of commands to create resources in the cluster. This is great for learning, testing, and troubleshooting. Using the declarative way, you define the resources needed in YAML files and use kubectl to send the content of these files as the desired state to the cluster. So instead of a series of commands, this is reproducible, and you can even store these YAML files in a source control system. Here, we can see a series of commands to create resources. That's the imperative way. You can create a pod using the run command, create a deployment or service using the create command. Using the declarative way, you would use a YAML file to define the resource and then send the content of that file to the cluster to create these resources. So, what's a YAML file? Well, it's a text file that contains properties that define the resource. It has some required properties like the API version, the object kind that defines the type of object you want to create. We'll take a look at these later on. You can use the kubectl create command to send the information to the Kubernetes cluster. We will take a deeper look at YAML files in further lectures, but right now you may be wondering, do you need to type all that YAML manually? The answer, of course, is no. One way to get the correct syntax is to copy one from the official Kubernetes documentation at kubernetes.io/docs. You then search for the object you want to create and click on the copy icon. Another way is to use templates offered with an editor like Visual Studio Code. Let's say you create a new YAML file, then you type Control Space and select the template to generate the manifest that you can edit. Neat. You can also use the Kubernetes CLI to generate a YAML. Add -- dry run equals client and -o for output, specifying a YAML to output the YAML to the console. You can even send the output to a file using the greater than sign and a file name. And this concludes this overview of the imperative and declarative ways to create resources in Kubernetes. Let's deploy an Nginx container using both the imperative way and the declarative way. Using the imperative way, we're going to type a command called kubectl create. We're going to create a deployment. Going to name our deployment, my Nginx one. And we're going to specify a parameter called image, where we will specify the image we want to run. This will create a deployment, and we can kubectl get a list of the deployments using kubectl get deploy, and there it is. Now, the second way is the declarative way. Instead of typing a command with all the parameters at the command line, we're going to specify a YAML file where all the configuration options are stored. kubectl create -f for file and the name of the file. So let's run this. Okay. It was created. Let's again type kubectl get deploy get both our deployments. And if we take a look at the YAML file, well, it's a YAML file, the type deployment, it has the my nginx2 name, it has a bunch of parameters that will come back to that a little bit later. But basically, all the configuration parameters are stored in that YAML file. What's cool with that concept is that you can put these files quite easily in a source control system. All right, let's do a little bit of a cleanup. Let's delete our deployment. kubectl delete deployment my nginx1. Okay, and I'm going to use the same command, but using a shortcut this time, kubectl delete deploy instead of deployment, and the name of our deployment. Okay, and if I type again kubectl get deploy, there's no deployments currently in my namespace. Let's take a look at namespaces. So, what is a namespace? It's a Kubernetes resource that allows you to group other resources. Let's say you need to deploy your application in multiple environments like dev, test, and prod. Well, you can create a namespace for each of these environments. They are like logical folders in which you group resources. Kubernetes creates a default namespace called, well, default. Objects in one namespace can access objects in a different one. The Kubernetes internal DNS assigns network names to some resources. Deleting a namespace will delete all its child objects. This is super useful when doing tests. Create a namespace in the morning, create resources under that namespace during the day, and at the end of the day, simply delete that namespace. This command lists all the namespaces existing in a cluster. We'll take a look at this command in more detail. Okay, first, you create a namespace. This YAML file defines a namespace called prod. Then, you use that namespace when you create other resources. In the metadata section, you set the namespace key to the name of the namespace you want this resource to be created in. So namespace, prod. You can assign network policies and limit the resources that you can create in a namespace using the resource quota object. Here's a cheat sheet for the namespace commands. So kubectl get namespace lists all the namespaces. And if you don't want to type namespace each time, you can use a shortcut, ns. So kubectl get ns is the same thing as kubectl get namespace. You can set the current context to use a namespace in the next commands that you'll type by using kubectl config set context current, which will use the current context, and then namespace equal the namespace that you want to use. So the next commands that you'll type will be under that namespace. kubectl create ns and the name of the namespace. So you create a namespace, you delete it using kubectl delete ns and the namespace name. And you can also list all the pods or the objects from another namespace. So kubectl get pods or any objects, and then you pass the flag -- all - namespaces that will list all the objects in all the different namespaces. And this concludes this look at namespaces. Let's see how to list and switch between namespaces. You can get a list of the namespaces using the kubectl get namespaces command. Let me copy this. And these are the namespaces currently created on my machine, on my Kubernetes cluster. So default, kube node, kube public, kube system. I can also use the shortcut for namespaces, which is just 2 letters, which is a lot faster to type. And it will give you the exact same result here. Let me get a list of the pods running. kubectl get pods. No resources found in default namespace. Means that I'm currently, my context is using the namespace called default, right? And there's no pods running in there. So what if I want to list the pods that are in the kube system namespace? Well, I can use the same command, kubectl get pods, specifying the namespace switch and specifying the name of the namespace. Let me copy this. And there are many pods running here. I can use also the shortcut. So instead of typing -- namespace equal, I can just use the shortcut -n. So only one dash here, 2 dashes here, and the name of the namespace. So let's try this. And it works. Perfect. Now, what if I want to change from the default namespace or the namespace called default to a namespace called kube system, right? And then apply all my commands so all the objects will be created in that namespace. Well, I can do that by using the kubectl config set context -- current. So here we're modifying the context and passing a switch called namespace and the name of the namespace we want to change. So we want to change, instead of being the default namespace all the time, we want to be in the kube system. Okay. And now let's see if we run kubectl get pods, if we would get some pods. Of course, because we're currently in that kube system namespace. Okay, now let's change back to the default namespace. And let's get a list of the pods. There should be none. Perfect. Okay, so this is how you change namespaces. Perfect. Of course, we can create new namespaces by using the kubectl create ns for short for namespace and a namespace name. So hello. Okay, kubectl get ns, and my namespace here was created 7 seconds ago. And I can delete a namespace using kubectl delete ns and the namespace name. Copy that. And hello. Now, a bit of a warning here. If you have resources under that namespace, these resources, the pods, the containers, whatever running, will also be deleted. So use this command with caution. Take a couple of seconds. Okay, let's get the namespaces, and our hello namespace is gone. Let's now look at the master node. A node is a physical or virtual machine. A group of nodes forms a cluster. The master node is also called the control plane. The Kubernetes services and controller are located on the control plane. They are also called the master components. And you usually don't run your application containers on the master node. etcd is a key value data store where the state of the cluster is stored. The API server is the only component that communicates with etcd. Let's start with the API server. It exposes a REST interface, and client tools like the Kubernetes CLI communicates through that REST API. It saves the state in etcd, and all client interacts with the API server, never directly with the data store. etcd is the data store for storing the cluster state. It's not a database, but a key value store. It's the single source of truth inside Kubernetes. The Kube Control Manager is the controller of controllers. Its job is to run the other Kubernetes controllers. The Cloud Control Manager job is to interact with the cloud providers. It checks if nodes were created or deleted, route traffic, create or delete load balancers, and interact with the cloud provider's storage services. The Kube Scheduler watches for pods that are not created yet and selects a node for them to run on. It checks for various rules and then assigns the pod creation to a node. Finally, you can install various add-ons on the master node. These add-ons provide additional functionalities in your Kubernetes cluster. And this concludes this look at the master node. Let's take a look at the worker nodes. A node is a physical or virtual machine. A group of nodes forms a cluster. There's a special node called the master node, sometimes called the control plane, where the Kubernetes services are installed. The nodes running the containers are called the worker nodes. When a worker node is added to the cluster, some Kubernetes services are installed automatically. The container runtime, the kubelet, and the kube proxy. These are services necessary to run pods, and they are managed by the master components on the master node. The kubelet manages the pod's lifecycle and ensures that the containers described in the pod specifications are running and are healthy. The kube proxy is a network proxy that manages network rules on nodes. All network traffic goes through the kube proxy. On each node, you will find a container runtime. Kubernetes supports several container runtimes that implements the Kubernetes Container Runtime Interface Specification, or CRI. One thing to note is that for Kubernetes version previous to 1.19, the Moby Container Runtime was installed and was receiving the Container Runtime Interface call through a shim because it did not fully implemented the specifications. This is not ideal as it added an extra step. Starting with Kubernetes version 1.19, Moby is no longer installed. Oh, wait a minute. Moby not installed, that means that my Docker containers will no longer run if the Docker container runtime is not installed, right? Well, the short answer is that your Docker images will run as is. Nothing to change. It's business as usual. What changed is that what you can do inside the cluster. Since the Docker runtime is no longer installed, you no longer can access the Docker engine and issue Docker commands directly inside a node. You'll have to use another tool called creectl, but again, that's if you SSH into a node and run commands directly on that node, something that you don't do usually. All right. A node pool is a group of virtual machines, all with the same size. A cluster can have many node pools, and each node pool can host virtual machines of different sizes. Let's say that we have two node pools in our cluster. The first one consists of VM without GPUs, and the second one with GPUs. Remember that Docker Desktop is limited to one node, so basically you run the master components and all the application containers on the same node. And this concludes this look at the worker nodes. So let's get some information about our nodes. I'm going to run a kubectl get nodes. And since I'm running on Docker Desktop locally here, I have only one node. Name is Docker Desktop, status is ready, role is master. Here's the revision, the version number, and it was installed 72 days ago. All right. I can get more information about the node. Since I only have one node, I can skip the node name parameter. And here's a bunch of information. The name, the role, some labels, creation date. What else? The capacity to CPUs. Number of pods, maximum number of pods that I can run, 110. The architecture, the OS, Linux, architecture AMD, the pods running, and the CPU request, CPU limits, memory. So all useful information when you need to troubleshoot and debug. So that's pretty interesting. Now, I'm using locally Docker Desktop, so I'm limited to one node. Let's switch to my demo cluster running in the cloud. So let's do the same thing. kubectl get nodes. Aha, have more nodes now. So I have a cluster in the cloud running 3 nodes in a node pool. So 1, 2, 3, status ready, agent, and the version of Kubernetes that is running. That's interesting. Let me grab kubectl describe node, and let's say use this one. So I can get the same information that I was getting earlier, but this one is running in the cloud. That's the name, role agent pool, the different labels, annotation, the number of CPUs, memory, system info, it's running Ubuntu, Linux, AMD 64. What else? And the different pods that are running on this node. Let's take a look at pods. So, what are pods? A pod is the smallest unit of work in Kubernetes. It encapsulates an application container and represents a unit of deployment. Pods can run one or more containers. Inside a pod, containers share the same IP address space and volumes, and they communicate with each other using localhost. That's inside the pod. Pods are ephemeral. Deploying a pod is an atomic operation, so it succeeds or not. If a pod crashes, It is replaced by a brand new one with a shiny new IP address. You don't update a pod that is currently running. You create an updated version, deleting the first one and deploying the new one. You scale by adding more pods, not more containers inside a pod. I used this analogy in a previous lecture. Pods are like cattle, they are ephemeris, and you just replace them. A node can run many pods, and a pod can run one or more containers. If a pod runs multiple containers, there's usually one that is the main worker, where your application logic is located. And the other ones are helper containers that provide services to the main worker. We will come back to this concept in another lecture. And this concludes this look at pods. Let's take a look at the pod lifecycle. We'll start with the creation lifecycle. So, when you issue a kubectl create command to deploy a pod in your cluster, the CLI sends the information to the API server, and that information will be written into etcd. The scheduler will watch for this type of information, look at the nodes, and find one where to schedule the pod and write that information, of course, in etcd. The kubelet running on the node will watch for that information and issue a command to create an instance of the container inside the pod. And finally, the status will be written in etcd. One thing to notice is that each time an operation is taking place inside the cluster, the state is written in etcd. So etcd is the single source of truth in the cluster. All right, so let's take a look at the deletion lifecycle now. When you issue a kubectl delete command to delete a pod from your cluster, the CLI sends the information, of course, to the API server. That information will be written in etcd. And notice that a grace period of 30 seconds will be added. So the kubelet picks that information and sends a terminate signal to the container. If the container hangs, it is killed after the 30-second grace period. And finally, the state is stored in etcd. The pod state will give you a high-level summary of where the pod is in its life cycle. Pending means that the pod is scheduled for creation, but is not created yet. If you run out of resources in your cluster, Kubernetes may not be able to create new pods. And if this happens, the pods will be in the pending state. Running means that the pod is currently running. Succeeded means that the code exited without any errors. Fail means that the code inside the pod exited with a non-zero status, so some kind of error occurred. Unknown means that Kubernetes can communicate with the pod. And finally, crash, loop, backoff. Oh, I love this, this state name. So crash, loop, backoff means that the pod started, then crashed. Kubernetes started it again, and then the pod crashed again. So Kubernetes said, okay, hold on, I'm stopping here. So we'll take a look in a future later of where to look for these states. And this concludes this look at the pod life cycles. Let's see how to define and run pods. To define a pod the declarative way, you create a YAML file specifying pod as the kind. That's the type of resource you want to create. You specify an image location. In this case, the Nginx image will be pulled from Docker Hub. That's the default container registry. You set the port that the container will listen on. You can add labels. They are used to identify, describe, and group related sets of objects and resources. You can set environment variables directly here. Might not be the best idea to place configuration values. In a later lecture, we'll see how we can externalize that by the use of a config map object. You can even specify a command to run when the container starts. If you have created a YAML file with your pod definition, you use kubectl create -f specifying the YAML file location and name, and this will create your pod the declarative way. Now, if you don't have a YAML file and you just want to run a pod the imperative way, you use kubectl run. You specify a name for your running pod, --image, the image name. You can specify a program to run. In that case, it's sh. And -c, you can specify a parameter that you want to pass to the program. kubectl get pods will list all the pods that are currently running. -o wide will get you the same information, but with a few columns more. kubectl describe pod and the pod name will show the pod information. You can use kubectl get pod with the pod name, -o for output in YAML format, and you can pipe that to a file name. So this is pretty cool because it will extract the pod definition in YAML and save it to a file. So if in case you lost that YAML file that was used to create a pod, well, you can recreate it quite easily. kubectl exec-it specifying the pod name and the program to run will get you inside that pod in the interactive mode. You delete a pod using kubectl delete -f specifying the YAML file, or if you don't have the YAML file, simply use kubectl delete pod and the pod name. That will result in the same as the previous command. And this concludes this look at how to define and run pods. In this lab, we will run our first pods. We'll start by using the imperative way. We'll use the kubectl run command, specifying the image that we want to run. In our case, we want to run an Nginx web server. And we'll specifying a name to the running instance, my Nginx. Let's run this. Pod my Nginx created. Let's get a list of the running pods by using the kubectl get pods command. I have one pod running, my Nginx. Ready 1 of 1, status running. It was created 11 seconds ago. Let's try to get more information by adding the -o wide parameter. It's the same command, but we'll get a little bit more information, like the IP address of the pod and the node where the pod is currently running. Awesome. If we want more information, we'll use the kubectl describe command with the type of object and the name of the running instance. So kubectl describe the type pod and the name my Nginx. All right, tons of cool information here. The name of the object, my Nginx, the namespace where it's running, the node where it's running, start time, any labels, annotation, the IP address, information about the container, any volumes, restarts that happened, and any volumes here. And at the end, we get the list of events that happened when the pod was created. It was first scheduled, and then the image was polled, and then the image was successfully polled and created, and then started. The kubectl describe command should be the first thing you try when doing some troubleshooting. Here, you will likely have some very useful information in case a pod doesn't start. Maybe the image is not available. Maybe the image didn't start correctly. So kubectl describe command, that's very, very useful. Let's now delete our pod by using the kubectl delete, the object type, pod, and the name of the running pod. Should get my command line back in a few seconds. All right. Let's now run a second pod, this time a busybox image. kubectl run the image, busybox, and the name of the running instance, my box, but we're adding extra parameters here, -it, -- the program we want to run. This will open a session inside our running pod. And look at the command prompt. It's changed to a $. This means that now I can type commands that are running inside the pod. ls for listing the folders and files. I can run a base64 command here. I can encode a string here. And that happened inside the running container, inside the pod. Pretty cool. To stop the session, simply type exit, and this ends the session. Okay, let's do a little bit of cleanup. In the busybox case, it takes up to 30 seconds to delete, so we have two options here. We can run the kubectl delete, the object type, and the running instance. And to get back our command prompt right away, we can use the -- wait = false parameter. Or if we simply want to kill the pod brutally, we use -- force and with a grace period of 0 seconds. Let's run this. And this will kill the pod brutally. All right. Let's now create a pod the declarative way by using a YAML file. We have a YAML file here called myapp.yaml. The kind is a pod. We give it a name, myapp-pod, a few labels, the image we want to run, any limits here for the resources in CPU and memory, the port that the container is listening to, and some environment variable. We're defining an environment variable called dbcon that will have a value of my connection string here. Awesome. Let's use the kubectl create -f for file and the name of our YAML file. Pod myapp-pod created. Perfect. Let's run the kubectl get pods command to get a list of our pods. It's running. Perfect. We can also describe our pod. Again, the same information that we saw earlier. right? The default namespace. And here, look, we have our environment variable and the same events that we saw earlier. Previously, we used the kubectl run command with the -it parameter to open a session to our busybox container. Now, what is the pod is currently running? Well, we can use the kubectl exec command with the same it parameter here. We specify the pod name and the program we want to run. That will open a session to a pod that is currently running. Okay, let's output the dbcon environment variable, my connection string. Awesome, that worked. So let's exit or stop our session. And this time we'll use the kubectl delete command, specifying our YAML file to delete our pod. Let's take a look at init containers. Let's say that your app has a dependency on something. It can be a database, an API, or some config files. You want to initialize or validate that these exist before launching the app, but you don't want to clutter your main logic with this type of infrastructure code. So what do? You can use an init container that lets you initialize a pod before an application container runs. Let's say that for the app container to run, it requires a series of configuration files. In the pod definition, you define a container that will run first. This is the init container. Upon completion, Kubernetes will start the app container. This is a great pattern for applications that have dependencies. The init container job can be as simple as validating that a service or a database is up and running. This keeps the infrastructure code out of the main logic. Init containers always run to completion. You can have more than one, and each must complete successfully before the next one starts. If it fails, the kubelet repeatedly restarts it until it succeeds, unless its restart policy is set to never. Probe are not supported as init containers run to completion. In this pod definition file, we have the main application located in the containers section in green, and the init containers in the init container section in yellow. As you can see here, we have two init containers. They both watch for services to be up and running. So the first one will run to completion, then the second one, and finally, Kubernetes will start the app container. And this concludes this look at init containers. In this lab, we will use an init container to modify the home page of an Nginx container. Let's take a look at our YAML file. It's manifest for a pod. We have two sections here, containers and init containers. Let's first take a look at init containers. We will use a busybox image, and we'll run this command wget, and we'll hit that website right here. And that website, it's the home of the first website, the home page of the first website. It's pretty simple, just a few lines of HTML. All right. And we will save that HTML into a file called index.html into a volume called work directory. And the Nginx image will map that volume and will serve that index.html page as its default web page. So basically, we're initializing our Nginx container by using an init container here. Awesome. Let's open a terminal. And let's deploy our application. kubectl apply -f, the name of our YAML file. Let's wait till the Nginx image is up. So if I do a docker ps, yep, my Nginx container is up. So let's open a session right into that Nginx container. And let's try to hit the default web page, curl localhost. And yep, that worked. We're serving the default web page of the CERN website here. Pretty cool. Let's type exit. And let's do our cleanup, kubectl delete, and our YAML file. Let's now look at selectors. When defining Kubernetes resources, you can use labels. These labels allow you to identify, describe, and group related set of objects or resources. They are simply key value pairs that you define yourself. In this pod definition, we see two labels: app with a value of my app, and type with a value of front end. Note that the app and type keys are not something defined by Kubernetes. They are defined by you for your application. Okay, but what does labels have to do with selectors? Well, selectors use labels to filter or select objects. Here we see a selector in this pod definition. The selector type is node selector, and the key value pair is this type equals superfast. Okay, but how does that work? Here we have a pod definition with the node selector set to this type equals superfast. We're telling Kubernetes that we want to run this pod on a node that has a label set to this type equals superfast. Node A does have such label, so Kubernetes will schedule the pod creation on that node. The simplest way to picture what selectors do is by comparing them with a SQL query. It would be something like select star from nodes where this type equals superfast. And this concludes this look at the selectors concept. In this lab, we will test the selector concept. We have two YAML files here. The first one, it contains the definition of a pod. We will run an Nginx web server listening on port 80. And for the selector concept, what is interesting is this section, the labels section. So we have two labels defined here. app set to my app, type set to front-end. Let's take a look at the second YAML file. That's a service of name myService. It's listening on port 80 and targeting or redirecting the traffic to port 80 that the pod is listening on. And let's look at this section, selector, app my app, type, front -n. So these are the same labels that we define right here in our pod definition. All right, let's test this concept. I'll open a terminal and we'll first deploy our pod by using kubectl apply -f and the name of the YAML file. Let's now deploy the service, kubectl apply -f myservice.yaml. All right. How do we know that the service is connected to the pod? How do we know that the selection was successfully made? To find that, let's get the pod IP address by using kubectl get pod -o wide. And let's look at the IP address here, 10.1.9.31. All right. Let's run this command, kubectl get ep. EP is short for endpoint. And here's the name of our service, my service. So let's run this. All right. You see in the endpoints column, 10.1.9.31, that's the same IP address. Let's now try to port forward to that service. Okay, we get an immediate result here. And let's go to localhost port 8080, and that worked. Perfect. Let's go back here to our terminal, and let's type Control-C to stop the port forward. Now, let's try to break things a little bit. We'll open the myapp.yaml file, and let's change one of the labels. So app will set it to myapp2. Control-S, let's save that file. And let's redeploy the file again, the pod again, by using kubectl apply -f and the name of the YAML file. All right. Let's check the endpoint again. Is it still working? Aha! Look at the endpoint column, none. And if we try to port forward again, there's no immediate result, so that doesn't work. So this proves that both labels must match here. The selector here, both labels must match the labels in the pod definition so that the selection can work. All right, let's type Control-C to stop this. And let's do our little cleanup by deleting the service and then the pod. Let's take a look at multi-container pods. We saw in a previous lecture that pods can run one or more containers, that there's always a main worker, and that the other containers are providing services to that main worker, like saving data to a database and writing log files. There are scenarios where multi-container pods make sense, and they are well documented in a series of patterns. We will take a look at some of them in the next few slides. With the sidecar pattern, the helper container provides extra functionalities to the main worker. Let's say that our app writes some log files inside the pod. The sidecar can copy these log files to some persistent storage offered by the cloud provider. This way, the application code located inside the main worker is not cluttered with infrastructure code. That code is located in the helper container. And if you move from one cloud provider to another one, well, you simply replace or update that helper code. This keeps your application code super clean. Our next pattern is the adapter. let's say that our main worker outputs some complex monitoring information that the monitoring service of our cloud provider cannot understand. The adapter role would be to connect to the main worker, simplify the data for the monitoring service. Again, the code specific to the cloud provider service is located inside the helper container. The ambassador pattern is another type of man-of-the-middle role. Let's say that our application code needs to write to some NoSQL database, but the code has no clue on how to do that. No problem. You can send that data to the ambassador. That in turn will write the data to the NoSQL data store. The code specific to the data store service is located inside the helper container. If you're curious about these patterns, I suggest you get a copy of the Design Distributed Systems book. The author is Brendan Burns. Brendan worked at Google where he co-created Kubernetes. He now works at Microsoft. So, how can you define multi-container pods? Well, if you remember the lecture about YAML files, you see that the container sections is actually a list. This means that you can define multiple containers. Highlighted in yellow, you see container number 1, and in green, container number 2. And when you create a pod, both containers will be created at the same time. Pretty cool. Here's a quick cheat sheet for multi-container pods. So after you created your YAML file, you simply use kubectl create-f, specifying the YAML file name. So same thing as creating a single container pod. If you want to exec into one of the container, you simply use kubectl exec-it, the pod name, and specifying -c and the container name. This way, you can jump into one of the containers running inside the pod. You get the logs for a container using kubectl logs, the pod name, -c, the container name. And this concludes this look at multi-container pods. Let's take a look at some networking concepts. Kubernetes is what we call a flat network. As a result, most resources inside a cluster can see each other. All containers within a pod can communicate with each other. All pods can communicate with each other. All nodes can communicate with all pods and all nodes. Pods are giving an ephemeral IP address while services are giving a persistent IP. So this is quite important. We'll come back to that later. Let's illustrate the cluster network in blue here. Each pod gets an IP address, and the containers inside a pod share the same address space. The containers inside the same pod share the same IP address, but each must be assigned a different port number. They can communicate inside the pod using localhost and the port number. They can also share the shared volumes. What about communications between pods? Can the container on the right talk to the container inside the pod on the left using localhost? No, they can't. They need to go through a service that will front the network traffic for the pod. For external access to the cluster, traffic goes through a load balancer service offered by the cloud provider. In future lectures, we'll look at different types of services that we can use in Kubernetes. And this concludes this quick look at networking concepts. Let's create a multi-container pod using a YAML file. Let's take a look at the YAML file. So the kind is pod. The name will be 2-containers. And in the containers section, we're defining two containers. So the first one will use the Nginx image, and we'll name it my Nginx. And that web server will listen on port 80. And we're defining a second container using the BusyBox image, and we'll name it my box. This one will listen on port 81. And for the BusyBox container to stay up and running, we need to tell it to stay up by issuing a sleep command. So it'll sleep for an hour. What we'll try to achieve is open a session on the BusyBox container and try to hit the Nginx container. So the default web page served by the Nginx container. All right. Let's try to create our pod here using kubectl create and the name of our YAML file. Okay, pod 2-containers created. So let's try to see if they're running. All right, 2 out of 2, because we have 2 containers running in that pod. Status running, 10 seconds. The IP address. So there's one IP address assigned to the pod and the node. Okay, let's try to get a little bit more information by using the kubectl describe pod and the name of the pod. Let's scroll up a little bit. So the name is 2-containers. Namespace is the default one. The node where it's running. The containers. So the first one is my Nginx, which using the Nginx image. We have information about the limits that we set earlier in the YAML file. My box using a BusyBox image, listening on port 81. Right? There's that sleep command. So useful information here. And also look at the events now. So earlier, when we add only one container inside a pod, we would get just one set of events for polling and creating the container. Now we have 2. First one is the pod was scheduled. And the second one here on the second line, the Nginx image was in the polling state. It was polled, created, started, and then the BusyBox container was polled and created. Okay. Perfect. Now let's try to open a session inside our BusyBox container. So we'll use kubectl exec-it. Okay, here's the trick now. We need to specify the pod name and then the container name that we want to connect to, and then the program that we want to run. That's the trick. When you have multiple containers, you need to specify the pod name and then the container name. All right, let's try to do that. Oh, looks good. At last, yeah, it worked. Okay, now we'll use wget to try to hit that default page served by the Nginx web server. Wget with this flag, and we'll call localhost. All right, welcome to Nginx. So that worked. Now, I'll pause for a couple of seconds, and I'm going to ask you, why did that work? Why calling localhost worked? So that worked because, let's go back to our YAML file. The Nginx container is listening on port 80, right? We don't have to specify a port number here. If the Nginx container would have listened to something different, we would have to specify here localhost, colon, and the port number. All right, let's try to exit this. Perfect. Let's now delete our pod using kubectl delete and the name of the YAML file. And by using the force and grace period equals 0 flag, that will kill both containers immediately. Perfect. This is a super short lecture just to introduce you to the concept of a workload. So a workload is an application running on Kubernetes. All containers running in a Kubernetes cluster must run in a workload. The pod is the atomic workload. It represents a set of running containers, and all workloads will create pods. The replica set and the deployment will provide extra functionalities on top of the pod, like the ability to define how many instances of a pod we want. The stateful set and the daemon set are specialized workloads. And finally, the job and cron job offer tasks that run to completion. These are short-lived tasks. We will see each of these workloads in detail in the following lectures. And this concludes this super short lecture on the workload concept. Let's take a look at replica set. The replica set primary job is to manage the pod replicas, making sure that the desired number of instances are running. This provides the self-healing capabilities in Kubernetes. While you can create replica set, the recommended workload is the deployment. We'll come back to that in a moment. So let's say that you want 3 instances of a pod to run at all time. You create a replica set and specify that you want 3 replicas. If for some reason one pod crashes, Kubernetes will replace it automatically without any human intervention. Pretty cool, eh? Let's see how to define a replica set by starting with a pod. We take the pod definition, except for the API version and kind, and we place these values in the template section of the replica set. The final result is a replica set YAML file. So basically, in the section highlighted in green, you will find values specific to replica set, and under the template section, the values that define the pod you want to run. Here, you set the desired number of instances with the replicas property. Again, while you can create replica sets, the recommended workload to use is the deployment because it provides extra functionalities on top of the replica set. So why bother and learn about replica sets? Well, in the deployment lecture, you'll see that when you create a deployment, that will also create a replica set in the background. That's why it's important to learn about the replica set's functionalities. Here's a cheat sheet for replica sets command. You create one using kubectl apply-f and the YAML file. You get a list of the replica sets by using kubectl get rs. You get some information about a replica set by using kubectl describe rs and the replica set name. You delete one using kubectl delete. If you have the YAML file, you specify -f and the YAML file name, or if you don't have the YAML file, simply by using the replica set name, using kubectl delete rs and the replica set name. And this concludes this look at replica sets. Let's create 3 instances of an Nginx container using the replica set template. So let's take a look at our YAML file. The type of object we want to create is the replica set. This will be the name of the replica set, rs-example. We want 3 replicas running at the same time. And we want 3 replicas of this container. Name will be Nginx, and the image Nginx :Alpine. So it's a smaller version. And we define the resources and also the ports that each is listening on. All right. Let's try to create that. So kubectl apply or create -f and the name of our YAML file. Okay, replica set created. Let's take a look at our running pods and have 3 pods running. Okay, and look at the names that were assigned to each of these pods. rs-example, and then is some kind of a unique number here. Each one must have a different or unique name. So each one is ready, running, and look here, each one has a different IP address. Perfect. So let's take a look at our replica sets that we've created. So kubectl get rs. So there's one, rs-example, 3 desired, 3 current, 3 ready. Everything's green, everything's okay. Let's now describe our replica set. So kubectl describe rs for replica set and the name of our replica set. So let me paste that. All right, let's scroll up a little bit. So the name is rs-example. It's running in the default namespace. Any labels or annotations are listed here. Number of replicas that we set, so 3 current, 3 desired, and the current pod, the status is 3 running and 0 failed. The container information, so Nginx, we want to run an Nginx Alpine image, listing on port 80, the limits, and so on, and these are the events that were raised here. So each pod was successfully created here. All right. So last thing, we need to delete what created using kubectl delete -f and the name of the YAML file. Let's take a look at deployments. We'll start by comparing pods and deployments. Pods don't self-heal, meaning that if a pod dies, Kubernetes will not replace it automatically. Using a pod definition, only one instance can be created, and you can't update and roll back pods. Deployment can. A deployment manages a single pod template, so you create one for each microservice you want to run. When creating a deployment, this will also create a replica set in the background. But while you can see it, you don't interact with the replica set directly. You let the deployment manage that for you. To summarize, the replica set provides the self-healing and scaling functionalities, while the deployment provides updates and rollback functionalities. Let's take a look at the deployment definition. You define the desired number of instances with the replicas property. This will be used by the underlying replica set. You set the number of iterations to keep using the revision history limit property. And you set the update strategy in the strategy section. You can set the strategy type to a rolling update. This way, Kubernetes will cycle when updating the pods. The other strategy is recreate. Kubernetes will take all existing pods down before creating the new ones. We'll have a dedicated lecture on this topic later on. Like a replica set, we start with a pod definition, and we stuff the metadata section in the template section of the deployment. The final deployment definition looks like this. Highlighted in green, we see the properties specific to the deployment, and in yellow, the ones defining the pod we want to run. Here's a cheat sheet for deployments command. So if you don't want to use a YAML file, you can create a deployment using the imperative way. So you use kubectl create, deploy, you specify a name. Then with the image property, you specify the image, replicas, the number of replicas you want to run. And you can specify also other properties like the port number that the pods will listen on. If you have a YAML file, well, you simply use kubectl apply -f and the YAML file. You get a list of the deployments using kubectl get deploy, and you get the deployment info using kubectl describe, deploy, and the deployment name. Since a deployment will create also a replica set, you can get the list of the replica set using kubectl get rs. And you delete a deployment by using a YAML file. So kubectl delete -f, the name of the YAML file. Or if you don't have it, simply use kubectl delete deploy and the deployment name. And this concludes this look at deployments. Let's use the deployment template to create 3 instances of an Nginx container. So let's take a look at the YAML file. This time, we want to use the deployment kind. Type of object we want to create is a deployment. We name it deploy example. We want 3 instances, 3 replicas. And we want to keep 3 versions, 3 replica sets versions in the history inside Kubernetes. And if we scroll down a little bit, we see that we want to run an Nginx, the Alpine version, because it's a little bit smaller. And we name it Nginx. We set some resource limits, and each pod will listen on port 80. All right, quite similar to the replica set template that we saw earlier, except maybe for this parameter here. All right. Now let's create our deployment using kubectl apply or create -f deploy example. And let's get a list of the pods that are currently running. Kubectl get pods -o wide. And yes, we have 3 pods, 3 lines here. So look at the names given to each pod. So deploy example, that's the name of the deployment object. The name of the deployment object dash something unique. So to make sure that each pod has a unique name, Kubernetes has a random number like this. Only one container is running inside each pod. It's in running state. Each pod gets its own IP address. So that's perfect. Okay, let's now try to describe our pods. So we can use the kubectl describe pod and deploy example name. But we just saw that the names work a little bit different. Let's see if this works. Yep, it worked. It worked because the name is shared across these 3 pods, And so we get information about each one of these. Let's say I just need the information about that particular pod. I can use that name, the unique name also. So instead of deploy example, I'm going to use the full name. And there it is. I have the information about that pod, just that pod. All right. Let's now get some information about the deployment currently inside my cluster. So kubectl get deploy. I have only one deploy dash example, 3 out of 3 ready, up to date, available. So everything's looking good. And I can describe my deployment using kubectl describe the name of the type of the object and then its name. All right, so let's go a little bit. We have the name, the namespace, where it's running, any labels, annotations, number of replicas, 3 desired, 3 updated, 3 total, 3 available. Perfect. Strategy is rolling update. Okay, because we haven't set a rolling update strategy. That's the default one. We'll come back to that later on. The pod template, Nginx, Alpine, listening on port 80, right? And the events here. All right. Since a deployment will automatically create a replica set, let's take a look at the replica set that was created. So kubectl get rs, and for sure we have one replica set that was created by the deployment. 3 desired, 3 current, 3 ready. Everything looks okay. And we can also describe our replica set. Since we have only one, we can use kubectl describe rs, or we can use its full name. We copy that. And here I have the replica set description. And finally, we need to do a little bit of cleanup. We delete our deployment using kubectl delete and with the name of the YAML file. Let's take a look at daemon sets. The daemon set is a specialized workload. Its role is to ensure that an instance of a pod is running on all nodes. The pods are scheduled by the scheduler controller and run by the daemon controller. As nodes are added to the cluster, the pods are added to them. Typical use are running some kind of a helper service like a log collection or some kind of monitoring. Well, let's illustrate that. In this cluster, we have 2 nodes, and the daemon workload ensures that an instance of a pod is running on each one of these nodes. So you define a daemon set in a YAML file. You can specify that you don't want to schedule a pod on the master node by using a toleration. Same thing if you want to run the pod on specific node pools. Here's a cheat sheet for the daemon sets command. So you create a daemon set using a YAML file with the kubectl apply-f command. You get a list of daemon set using kubectl get ds. You get some information about a running daemon set using kubectl describe ds and the name of the daemon set. And when you want to delete a daemon set, you either use a YAML file using kubectl delete-f and the name of the YAML file, or the name of the running daemon set by using kubectl delete ds and the daemon set name. And this concludes this look at daemon sets. Let's run a busybox image as a daemon set to ensure that we have one instance of that container running on each node in our cluster. So let's take a look at the YAML file. All right. The kind is daemon set. We give it a name, daemon set-example. And the container that we'll run is a busybox. And here in the toleration section, we specify that we don't want to schedule a daemon set on a node role that is master. So we don't want to run that daemon set, that the busybox on the control plane on the master node. All right. Let's deploy our daemon set. So here I'll be deploying that daemon set on a cluster in the cloud that has 3 nodes, because if I would try to do that on Docker desktop with just 1 node, won't be interesting. So let's try to do that. Doesn't matter what cloud provider I'm using right now. Okay, let's get a kubectl get pods. We'll come back to the rest just after that. So here have 3 pods, daemon example with a unique name here. Let's add the -o wide flag. Let's examine the node column. So you can see that each pod is running on a unique node. So 0, 3, and 4 here. And this selector is interesting because if you have multiple objects, you can basically filter out or just select what you want. So here, selector says the app equals the daemon set example. That's the name of our object here. So that worked. One instance of our busybox is running on each node. Let me add a 4th node. All right. So my node count is now 4. Let's go back to Visual Studio Code and let's rerun the getpods command. And for sure, have a 4th instance of my busybox container running as a daemon set on the new node. Without me doing anything, it was deployed automatically because I selected the daemon set object type. Now we simply need to delete that daemon set using kubectl delete. Let's take a look at stateful sets. Let's say that you run a database inside your Kubernetes cluster. Traffic gets higher and you need to scale that database. So you create more instances. The main one can read and write, while the other instances are in read-only mode and use replicas of the main database. This is a complex scenario to implement. The stateful set role is to help you solve this complex problem. For pods that need to maintain state, and unlike a deployment, a stateful set maintains a sticky identity with a persistent identifier for each of the pods. And if a pod dies, it will be replaced by another one using the same identifier. The stateful set will create the pods in sequence and delete them in reverse order. Typical use are for network-related services that maintain some state, and also for databases. Each pod gets a unique identifier using the stateful set name plus the sequence number, and if one dies, it is replaced by a new one but with the same identifier. The pod creation is done in a ordered way, meaning that the first one will be created, then the second one, and so on. And when they are deleted in the reverse order. Note that the persistent volumes are not automatically deleted. To use a stateful set, you need to use an headless service. You define one by setting the cluster IP value to none. The stateful set will then refer to the headless service. And you define cloud storage in the volume claim templates section. Let's revisit this slide. As you can see, only the first pod lets you read and write. So how can you reach it if you want to write to the database? Well, you use the pod network name, in this case, the instance name, MySQL-0, plus the service name, so .MySQL. When reading, simply use the service name. This will load balance the calls across all instances. A bit of warning here. Containers are stateless by default, and stateful sets are offering a solution for a stateful scenario, but a lot of work has to be done on top of that. A better approach might be to use the cloud provider database services instead of trying to fit a stateful scenario inside your Kubernetes cluster. Lastly, deleting a stateful set will not delete the PVCs. You have to do this manually. Here's a cheat sheet for stateful set commands. So you create one using the kubectl apply-f and the YAML file. You get a list of stateful sets using kubectl get sts. You describe one using kubectl describe scs and the stateful set name. And you delete a stateful set using the delete command, either using a YAML file or the name of the stateful set. And this concludes this look at stateful sets. Let's now create a stateful set. Let's take a look at the stateful set.yaml file. There are two parts in this YAML file. The first part is the creation of a headless service. The kind is service, but the trick here is to set cluster IP to none, like this. This will create an headless service. All right. Second part is to create our stateful set. So the kind stateful set, give it a name, nginx-sts. And here, we're referencing our headless service here. So the name of our headless service assigned to the service name property. We want 3 replicas, right, of a nginx image. And we're creating a claim on a storage class name called Azure File. So the cloud provider here is not important. That will work on any cloud provider. So I already have a storage class name called Azure File. We'll use the read-write once access mode, and we'll use 1 gigabyte of storage. And we'll mount this to a folder var www. All right. So let's create our stateful set here. kubectl apply-f stateful set.yaml. And quickly, let's do a kubectl get pods wide. And here you can see that the first instance is running. The second one is running. The third one is pending. So each instance will be created in a sequence. So the first one, 0, the second one, 1, the third one, 2. You can see by the age of each instances. So 19 seconds, 14, and 9 seconds. They are created in a sequence and deleted in a reverse order also. Here we can see that there's an IP address assigned to each of these. Let's take a look at the PVCs. We should have a PVC for each of these instances. And yes, SES 0, 1, and 2. So we can do a mapping 1 to 1 here. So for SES 0, we have a PVC called also SES 0. To prove that, let's describe the second one, let's say. So QCTL, describe pods, and the number 2. And let's see what the PVC is assigned, what claim is assigned. So here, the volume claim name SCS-2. Awesome. Okay. What we'll do, we'll create a file in that instance, the instance number 2, and we'll delete the pod. The pod will be recreated automatically, and we'll see if the file still exists. We'll also modify the default web page served by Nginx and see how we can reach that file, the default web page, from another instance. So let's open a session on the Nginx SCS2. Perfect. Let's cd in var our volume, and let's simply type echo and pipe that to a file called echo.txt. I do it ls, my file is there, get hello.txt. Yeah, perfect. Okay, first step, creating that file. Second step, modifying the default web page. Let's cd into the user share nginx HTML folder. And let's do an ls here. So here's the default page served by Nginx index.html. We will brutally replace that file by using cat and piping that to the file name and typing hello, enter, Control D on Windows to save the file. The file is there. If I simply do a cat index.html, yeah, okay, the file has been brutally replaced. Okay, we'll close our session on this instance. So SCS2, let's close our session. And let's open a session on the instance 0. Okay. Awesome. Let's try to hit that default HTML page, but on the instance number 2. So Nginx SCS2. So to do that, we'll need to use the web address Nginx SCS2. So that's the name of the instance, dot the name of the headless service. And that worked. Would only the pod name work? No, you need a combination of both the instance name and the headless service also. All right, let's exit our session here. Okay, let's try to delete the instance number 2. Okay, let's do a kubectl get pod. We have a new instance that was created 7 seconds ago. but the name of the instance is still the same. So instead of a random number here, by using a stateful set, this will ensure that the names will be the same. Okay, so let's open a session on the instance number 2. Let's ls var, and here's our file. Awesome. Let's do our cleanup. So we'll delete the stateful set, and we need to manually delete the PVCs because simply deleting the stateful set will not delete the PVCs. So let's do that. Let's take a look at jobs. Jobs are for short-lived task workloads. You start a job, it executes, and succeeds or fails. So jobs don't stay in memory. They don't wait for traffic. A job creates one or more pods and ensures that a specific number of them successfully terminate. The job tracks the successful pod completions and then marks the job as complete when the desired number of completion is reached. When using multiple pods, the job will create them one after the other. They can also run in parallel. This is a job definition. You define how many pods you want to run at the same time. You can set a deadline if needed, and the number of completions to reach to mark the job as complete. And you should set the restart policy to never. So here's a cheat sheet for the jobs command. You create a job the imperative way using kubectl create job, the job name, and the image name. Using the declarative way with a YAML file, you use kubectl apply-f and the YAML file name. You list the jobs by using kubectl get job. You get some information by using kubectl describe job and the job that is currently running. And you delete jobs with either a YAML file using kubectl delete-f or with the job name, kubectl delete job and the job name. And this concludes this look at jobs. In this lab, we will create a simple job. So let's take a look at the job YAML file. So the kind is job. So that's the type of object we're creating. The name, we're giving it hello. And what we will run is a busybox container. And when the container starts, it will echo hello from the job. Perfect. Something simple. Let's run this kubectl apply with the name of our YAML file. Perfect. The job was created. Okay, let's get a list of the jobs. There's one. Hello. Completion 1. So it ran. And duration was 2 seconds. Okay. Let's do a kubectl describe job, since we have only one job that will do the work. If not, we can type the job name, hello. And but let's take a look at name, hello, namespace default, annotation, and so on and so on. It ran one time, one succeeded. So that's our container. Successfully create and completed. Perfect. Now, we can get a list of the pods using kubectl get pods, and this is the pod that was created to run the job. It's still there. You see the status? Completed. But it's still there, so we can get to examine the log in case something went wrong. So we can do cube ctl logs and the name of the pod here. Hello from the job. That worked. So let's do our cleanup. Let's delete the job. Job is deleted. Do we have any pods left? None. Any jobs left? None. Perfect. Let's take a look at cron jobs. A cron job is a workload that runs jobs on a schedule. It's an extension of the job that we saw in the previous lecture. The schedule is defined using a cron-like syntax in UTC. And you can get more information about the cron syntax in this Wikipedia page. Here's a cron job definition. You set the schedule parameter to a cron schedule. So how do you know if a cron job ran successfully? Well, you need to look at the job history. By default, the last 3 successful jobs and the last failed job are kept. The pods will be in a stop state, and you'll be able to look at their logs. If you don't want to keep any history, you can set the successful job history limit to 0. So here's a cheat sheet for the cron job commands. You can create one using the imperative way. And if you have a YAML file, you use the kubectl apply-f and the name of the YAML file. You can get a list of the cron jobs currently running using kubectl get cj. You can get some information with kubectl describe cj, and you delete the cron job using its YAML file using kubectl delete-f and the YAML file name. And if you don't have the YAML file name, you can delete it using kubectl delete cj and the cron job that is currently running. And this concludes this look at cron jobs. So let's create a cron job. We'll take a look at the YAML file. Kind is a cron job. I'm going to name it hello cron. And we will give it a schedule. Only stars, it means that it will run every 60 seconds, every minute. That's the default. And we're going to run a busybox image, and it will echo this string. Okay. So let's create our job using kubectl apply. And we can get a list of the cron jobs using kubectl get cron jobs. Okay, so here we have the name, the schedule, if it's suspended, if it's active, the last time it ran, and we can get some information using kubectl describe cron job, and we pass its name, hello-cron. Here, this is super useful for troubleshooting. The name, the default namespace, it runs in the default namespace. We have the schedule here. How many jobs does it keep in its history? How many failed job is kept? Also, the command that will run. Can get a list of the pods. Okay, one pod ran, so hello cron with a unique value here. So it has completed. I'm going to pause to let it run a few times. All right. The job ran 3 times. Well, the last one is still running, container creating. Let me refresh that. So it's completed. Okay, now we can get the logs by using kubectl logs and then the job name, the pod name. So hello from the cron job. So by default, the last 3 run of the job are kept in the history, and you can configure that in the YAML file. Let's delete our cron job here. Perfect. And if again we type kubectl get pods, all the pods in the history basically are also deleted when you delete the cron job. Let's take a look at rolling updates. In a previous lecture, we saw that using deployments, you can set the number of pods instances using the replicas parameter and set a number of previous iterations of the deployment to keep in Kubernetes. We also saw that there are 2 update strategies, rolling update and recreate. Recreate is quite simple. Kubernetes will shut down all the running pods and create new ones after that. Rolling update will cycle through updating pods. All right, let's illustrate that. Using recreate, all previous pods are deleted, and the new pods will be created after that. This means that there might be a small period of time where your microservice might not be responsive. Using the rolling update strategy, a pod is deleted and replaced by a new one, then the next one, and so on. There are 2 values that you can set to help you with this process. Max search will tell Kubernetes how many pods can be created over the desired number of pods. Let's say that you want 3 instances in total. Setting max search to 1 will allow creation of 1 additional pod on top of these 3 desired ones, and this while the rolling update is running. Max unavailable is the opposite. It's the maximum number of pods that can be unavailable during the update process. Note that if you don't specify an update strategy in the deployment manifest, Kubernetes will use a default strategy of rolling update with max surge and max unavailable both set to 25%. So let's say that we want 3 instances of a pod, and we set max surge and max unavailable to 1. We're telling Kubernetes that it's okay to create 1 additional pod on top of the 3 desired one, and that it's okay to have 1 pod less than the 3 desired one. When done, the previous replica set is kept. You set how many you want to keep with the revision history limit property. Here's a cheat sheet for rolling updates. You create, of course, your deployment using kubectl apply-f and the name of your YAML file. You get the progress of the update using kubectl rollout status. You get the history of the deployment using kubectl rollout history deployment and the deployment name. You can roll back a deployment using kubectl rollout undo and the deployment name that will roll back to the previous version. Or if you want to roll back to a specific revision number, you add the to-revision parameter. And this concludes this look at rolling updates. In this lab, we will create a deployment and later on update it to a new version using a rolling update. So let's take a look at the YAML file. The kind of object we're using is a deployment called hello-dep. We want 3 replicas, and we're using a rolling update strategy here and setting max search to 1 and max unavailable to 1. We will deploy a container called hello-app, hello app, and that'll be version 1. And later on, we will update it to version 2. Okay, so let's create our deployment here. Okay, we can get the deployment status by using kubectl rollout status and the deployment name. The deployment was successfully rolled out. Let's take a look at our pods running. Okay, so I have 3 instances. Perfect. hello-dep 3 times. Excellent. Let's describe the deployment. So kubectl describe deploy and the deployment name. And let's try to find if we can get some information about the strategy. Yeah, here it is. Rolling update strategy, max unavailable. Oh, wow, the strategy type is right here. Rolling update. Rolling update strategy, max unavailable 1, max search to 1. So you can get that information that we set earlier in the YAML files. Okay. Let's now see if we have a replica set. Here's our replica set. And let's now update our YAML file and change the version of hello app to version 2. So just update to 2 and save the file. And we will use kubectl apply and with the same YAML file. Now, what I'm going to do, I'm using right now K9S. It's a terminal, a dashboard in a terminal, sorry. And to get the visual view of what will happen, basically. So right now I have 3 pods in green. These are the ones that are deployed. Let's apply our new deployment. I'm going to switch quickly to K9S, and you can see, oh, it happens so fast. But you saw that the new pods were created and the old ones were shut down. All right. Here I can have a deployment status. Everything's fine. If not, we would have some information. If the deployment would take longer, we would have some information printed here. Okay, how many replica sets do we have? We have 2. The current one, so that's the current one, and the previous one. By default, 3 versions are kept in history. We can get the deployment history by using kubectl rollout history and the deployment name. Okay, version 1, version 2. Okay, we're at version 2, and we want to downgrade, basically, or roll back to the previous version. So you can do that by using kubectl rollout undo and the deployment name. So by default, it will roll back to the previous version. Or if you have multiple versions and you know what version you want to roll back to, you can specify the flag to revision and the revision number as we see here. Let's do this one. Well, either one will do the same thing. Okay, let me switch to K9S and see what's happening. Oh, the other one, the older, well, the version 2 is terminating. New version is created. And we can get a deployment status here. Everything successfully rolled out. Okay. Let's now take a look at our replica sets. So we still have 2, right? The current one is now the first one that we deployed. All right, and we can do our cleanup by deleting the deployment using the YAML file. Let's take a look at blue-green deployments. So let's say that version 2 of our microservice contains some breaking changes, like a different database schema. What do you do? Using the rolling update strategy, you'll have both version 1 and version 2 of your app running at the same time. That might not work at all. So using the blue-green deployment pattern, that might help solve that problem. Blue identify what's in production, and green identify a new version currently deployed but not yet in production. Notice that the pods label contains the version number. When ready, simply update the service definition to point to the new version. And now, green is now in production. So, green becomes blue, and blue becomes green. Oh, great. This means that this pattern is solving the new database schema problem. Well, not entirely. You may still have to deal with some downtime while you update your database. And also another drawback is that since both versions of the microservices will be up and running at the same time, you need to have enough free resources in your cluster to make this possible. And this concludes this look at the blue-green deployments pattern. In this lab, we will create a blue-green deployment. We have 3 YAML files here. So let's take a look at the LODEP v1. It's a deployment. We want 3 replicas of a container of an image called LOApp 1.0. And here we're setting a label of app LOV1. Now let's take a look at the second one. It's basically the same thing. So deployment, 3 replicas, but it will use version 2 of our LOApp application, and we're setting the this label here, app to LOV2. All right. Let's take a look at our cluster IP manifest file. So the kind is service, and here's the selector app LOV1. We will deploy that, and later on we will change the cluster IP manifest to point to the newer version. Okay, so let's deploy version 1 of our pods. And let's also deploy our cluster IP service. So let's take a look at the list of the pods currently running. There are 3 pods, and also there should be, if I type kubectl get SVC, 1 cluster IP SVC front, that's the one I just deployed. Perfect. So let's do a quick port forward to connect to our cluster IP service. So we'll port forward the port 8080 that the cluster IP is listening to localhost 8080. Here, kubectl port forward service, the name of our service, 8080 to 8080. And let's hit localhost on port 8080 here. Okay. So here, hello world version 1.0. Excellent. Okay. Let's now deploy version 2. So right in my terminal, I'll hit Control C on my Windows keyboard to break that and gain my terminal back. Perfect. Let's deploy version 2. Okay. And let's get a list of our pods currently running. Should be 6. So I have both versions in memory at the same time. Okay. So that's one of the drawback of this technique, this blue-green deployment technique. Okay, let's now edit the cluster IP manifest file. So we will change the selector to select app on LO v2. Let's save the file and let's update our cluster IP service by using kubectl apply and the name of the YAML file. Yes. Okay. Let's port forward again. All right. Let's hit that localhost again. And there you go. V2. It worked. Let's do a little bit of a cleanup. Let's delete our first deployment, our second deployment, and also the cluster IP service. You can select the 3 lines at the same time. Let's take a look at the concept of service in Kubernetes. First, what problem do services try to solve? Well, if the pod in green need to reach the pod in purple, it needs to use its IP address. The problem is that pods get ephemeral IP addresses. If the pod in purple dies, well, you replace it, and the new one will have a different IP address. So we need a way to make these calls between pods a lot more robust. So back to the service. What exactly is a service? Well, it's a Kubernetes object that you define in a YAML file. But unlike pods that have ephemeral IP addresses, services get durable IP addresses, and also they get DNS names. They serve as ways to access pods. They're kind of a middleman, and they target pods using selectors. Here we have 4 pods and a service. The service selects the pods that have the zone label equals to prod and the version label equal to 1. The first pod satisfies the selector, the second one also, but not the third one, and not the last one. So only the first 2 are selected. So let's say we have 2 instances of a pod, and we place a service in front of them. If another pod needs to reach these ones, it will go through the service, and then the service will load balance the request to the instances. In Kubernetes, we can use these services, the cluster IP, the node port, and the load balancer. Note that the cluster IP is the default service. We will look at them in more detail in the next lectures. And this concludes this quick look at the concept of services in Kubernetes. Let's take a look at the cluster IP. So, what is a cluster IP? Well, it's the default service in Kubernetes. Its visibility is cluster internal. This means that it's not possible to use a cluster IP service to reach a microservice from the internet, from outside the cluster. In the cluster IP definition, you can set two different ports. Port is the port that the service will listen on, and target port is the port that the selected pods are listening on. So the cluster IP will route incoming traffic to that port. In this YAML file, the service listens on port 80 and route the traffic to port 8080. Traffic is load balanced across the selected pods. So when do you use a cluster IP service? Well, to provide a durable way to communicate with pods, but from inside the cluster. So let's illustrate this. Here we have a cluster IP service fronting 3 instances of a pod. It's impossible to reach it from outside the cluster, but it's okay. It's visible from inside the cluster. This cluster IP will listen on port 80 and select the pods using these two labels. Since the selected pods are listening on port 8080, the service target port must also be set to 8080. This way, the pods in green that want to communicate with the ones in purple, well, they go through the cluster IP service on port 80, and the service route the traffic to port 8080. So let's say you have multiple microservices. You place a cluster IP in front of each of them. Because a cluster IP service IP address is durable, while the pods ones are ephemeral. Here's a cheat sheet for cluster IP. So the first two commands are imperative commands. Let's say you already have a pod running and you want to expose it using a cluster IP. So you would use kubectl expose, po short for pod, the pod name, specifying the port and the target port, and you can also give a name to your service. If you have a deployment, you can also use kubectl expose, deploy, the deployment name, specifying the port and the target port. So both commands are imperative commands. If you have a YAML file, you would use kubectl apply -f and specifying the YAML file name. You can get a list of the services running using kubectl get svc. Get a little bit more information specifying the flag -o and wide. You can also describe the service using a kubectl describe svc and the service name. And you can delete the cluster IP service using the YAML file with kubectl delete -f and the name of the YAML file, or kubectl delete svc and the name of the service. And this concludes this look at the cluster IP. In this lab, we will deploy an Nginx container, front it with a cluster IP service, and then deploy a BusyBox container, open a session on that BusyBox container, and try to hit the web page served by the Nginx container, but through the cluster IP service. All right, let's take a look at our YAML file. We'll start with the deployment one. Kind is a deployment. We want 3 instances of the pod, and we will run the Nginx image, the Alpine version, and it will listen on port 80. Now, we're setting 2 labels here, and the cluster IP service will select the pods using these 2 labels. So app example, environment prod. All right. Let's take a look at our cluster IP. kind service. It's going to listen on port 8080, and it will redirect the traffic to port 80 on the Nginx containers. All right. The selector is here. So app example environment prod. So that will select our pods in our deployment. Perfect. So let's try to do that first. Let's deploy the service. And let's deploy the Nginx containers. Let's also deploy the BusyBox. And we can take a look at this. It's a kind of pod. The name is my box, and it'll run a BusyBox image. Okay. So now let's get a list of our pods currently running. We should add 4. 1, 2, 3, 4. So the first 3 ones are the deployment, the Nginx images, and the 4th one is the BusyBox. All right. Let's try to connect to the BusyBox container. Open a session by using kubectl exec mybox-it and the name of the program we want to run. Perfect, that worked. I type ls, yep. Okay, let's try to use the service to reach the Nginx pods. So wget and http svc example : 8080. So let's try to run that and see if it works. Okay, that worked. Why did it work? So what is that name here? If we go back to the cluster IP definition, that's the name of our service. And it's listening on port 8080. The service name, the port that is listening on. And that's it. We can now exit our session on our BusyBox, and we can delete our resources, the cluster IP, the deployment, and the pod. Let's take a look at the node port service. What is a node port? A node port extends the cluster IP service and provides extra functionalities. Its visibility is internal, like a cluster IP, but also external to the cluster. You can set a third port using the node port property. This is the port that the service will listen on outside the cluster. Note that the port must be in a range between 30,000 and 32,767. And if you don't specify a node port value, well, Kubernetes will assign one randomly. You then set the port and the target port properties like you do with a cluster IP. This sounds like a good way to expose our microservices to external traffic. But this range between 30,000 and 32,767 is kind of annoying because you can't set it to, let's say, port 80. And one requirement for using node ports is that nodes must have public IP addresses. To access your service, simply specify any node port IP address plus the node port, and the traffic will be routed to the right node port service inside the cluster. The way it works is that you set the pods and the service just like you did before with a cluster IP, but this time you also specify a port number in the node port property. External communication uses the node IP address and the port set with the node port property. Internal communication uses the port set in the port property, just like a cluster IP. Now let's take a look at our node port cheat sheet. If you already have a pod running in your cluster and you want to expose it using a node port service, simply use the kubectl expose po, the pod name, specifying the port and the target port, and the node port as the type. Now, you may wonder, where do you specify the node port number? Well, you can't. There's no properties letting you set know that value between 30,000 and 32,767. So Kubernetes will assign one randomly for you. Same thing for a deployment. Let's say you have a deployment already running in your cluster and you want to expose it using a node port. You use kubectl expose deploy, the deployment name, port, the target port, the type, which is node port, and you can specify a name also. You can define a node port in a YAML file and deploy it using kubectl apply-f, the name of the YAML file. You list the services using kubectl get svc, get more info adding -o wide. You can describe your service using kubectl describe svc and the service name. If you have a YAML file, you can delete it using that file using kubectl delete-f, the name of the YAML file, or you can delete your service using its name with kubectl delete svc and the service name. And this concludes this look at the node port service. In this lab, we will expose a deployment using a node port service. We have two YAML files. Let's take a look at them. The first one is for the deployment. We will deploy an Nginx image, the Alpine version, listening on port 80. And we will need two replicas. Perfect. Let's take a look at the node port YAML file. The kind is service, and the type is node port. And the selector will select our deployment. And here we set our node port 32410. Okay. Now let's open a terminal. And we'll start by the deployment, kubectl apply, and our YAML file. Next, our service, kubectl apply nodeport.yaml. Awesome. Let's make sure that our pods are running. kubectl get pods-o wide. Awesome. 2 pods, 2 instances of our Nginx container. All right. Now, since we're using Docker Desktop, the Docker Desktop node is mapped to localhost. To reach the node port service, we need to use localhost plus the node port. Let's try that. Localhost 32410. And it worked. Awesome. Now, when using a cloud provider, you would need to get a node IP address instead of using the local host. You would get that IP address by using kubectl get nodes-o wide. And here in the external IP address column, you would find the external IP address of the node. Awesome. Let's do our cleanup. Let's delete our node port and our deployment. Let's take a look at the concept of services in Kubernetes. What problem do services try to solve? Well, if the pod in green needs to reach the purple one, it needs to use its IP address. The problem is that pods are ephemeral. If the purple one dies, you need to replace it, and the new one will have a different IP address. We need a way to make these calls between pods more robust. So what exactly is a service? A service is a Kubernetes object that you define in a YAML manifest. Unlike pods that have ephemeral IP addresses, services get durable IP addresses and a DNS name. They serve as a way to access pods, and they target pods using selectors. Here, we have 4 pods and a service. The service selects the pods that have the zone label equals to prod and the version label equals to v1. The first pod satisfies the selector, the second one also, but not the third one, and the last one. Only the first 2 are selected. Let's say that we have 2 instances of a pod, and we place a service in front of them. If another pod needs to reach these pods, it will go through the service, and the service will load balance the request to these instances. In Kubernetes, we can use these services: the cluster IP, the node port, the load balancer, and the ingress. The cluster IP is the default service. Its visibility is internal only. The node port can expose a pod outside the cluster. The load balancer and the ingress are similar services. They let you expose applications outside of the cluster. One operates at the layer 4 and the other at layer 7. L4, L7, what's that? The load balancer operates at the layer 4. That's the TCP transport level, so that's very low in the transport stack. It means that the load balancer can do simple operations like round-robin routing. The ingress operates at a higher level in the transport stack. Think of protocols like HTTP or SMTP. It's more intelligent, so you can configure complex routing rules. Okay, no worries if this sounds complex. For now, simply remember that an ingress is like a load balancer, but more intelligent. And this concludes this look at the concept of services. In this lab, we will create a load balancer service. But you may be asking yourself, we're not using a cloud provider right now. How can that work? Well, Docker Desktop is helping us. It will emulate the load balancer service, so we can test our load balancer locally. Awesome. Let's take a look at the application. It's a simple deployment. We want 2 replicas, 2 instances of an Nginx image. Super simple. And the load balancer YAML file, kind is service, the type is load balancer. It will listen on port 8080 and redirect traffic to the pod that is listening on port 80. All right. So let's open a terminal. And let's deploy the app and the load balancer. Perfect. Let's make sure that our pod are running by using kubectl get pods. Yes, I have my 2 pods are here. Perfect. Now, to get the IP address of the load balancer, we use kubectl get svc-o wide. And since we're using Docker Desktop will use localhost as the IP address. Using a cloud provider load balancer service, you would find here, instead of localhost, the public IP address of the load balancer. So let's test this. Open a browser and type localhost 8080. And that works. We reach our Nginx pod. Awesome. Let's do our cleanup. Let's delete our load balancer. and our application. This is an introduction to the persistent concepts in Kubernetes. We saw this slide earlier. Containers are ephemeral and stateless, and any data stored in them is deleted when the container is destroyed. So we need to find a way to store data outside the containers if you want to keep that data. So volumes let containers store data into external storage systems. These are storage services offered by the cloud providers. The vendors create plugins according to a specification called the Container Storage Interface. And there are two ways to use storage in the cloud, the static way and the dynamic way. We have separate lectures on these later on. All right, the cloud providers create plugins to expose their storage services as persistent volumes and storage class. These two are Kubernetes objects. Next, we will look at the static and dynamic ways. Let's see how to use the static way. Persistent volumes, or PV, and persistent volume claims, or PVCs, are two Kubernetes objects that let you define and use external storage. A persistent volume represents a storage resource that is available cluster-wide and is provisioned by the cluster administrator. You then use a persistent volume claim to claim the persistent volume. A pod will then use the PVC to mount a local folder. PVCs can be used by multiple pods, and inside the pods, all the containers are sharing the same volume. There are many persistent volumes plugins available. Some are offered by the cloud providers. The one highlighted in yellow called HostPath is a special one. It's a plugin available with Kubernetes that allows you to do local testing, and it's not mapped to a cloud provider storage service. It will not work in a multi-node cluster, but it's super useful for local testing. Here's the main drawback of persistent volumes. Let's say that the cluster admin provision 100 gigabytes of storage, and that the pod only requires a small portion of this storage. Let's say just 1 gigabyte of that 100 gigabytes in total. So just 1 gigabyte. Well, too bad for the other pods, because the volume is used exclusively by the pod who has the claim on it. This can be a waste of precious resources, and we will see how storage class get around this problem in the next lecture. Okay, in the meantime, let's focus on the PV and the PVC. You first select the cloud provider's storage service you want to use. Then, you create a persistent volume and set the required capacity, let's say here 10 gigabytes. You then create a PVC, so a claim, that refers to the persistent volume. And finally, you use the PVC from your pod and mount a local folder on it. There's an important property that you must be aware of. It's the reclaim policy. Set at delete, all data will be lost when the claim on the volume is released. And this is the default value, so be aware of this. If you want to keep your files when the PVC is released, you have to set the reclaim policy to retain. Again, the default value is delete, so be careful and be aware of this. There are three access modes possible. Using read-write many, the volume can be mounted as read-write by many pods. Using read-only many, the volume can be mounted read-only by many pods. And finally, with read-write once, the volume can be mounted as read-write, by one single pod, and the other pods will be in read-only mode. This might be useful if you have a main worker that writes data and the other pods simply read the data. You define a persistent volume using the persistent volume kind, and you specify the capacity, the access mode, and the reclaim policy in the spec section. In this example, the hostpath plugin is used to access local storage. Remember to only use hostpath for local testing and refer to the storage provider documentation on how to create a persistent volume specific for their storage service. You then define a claim, so a persistent volume claim, making sure that the access mode match the one set in the persistent volume. In this case, the claim is for 8 gigabytes out of the possible 10 gigabytes set on the persistent volume. This means that no one can claim the remaining 2 gigabytes until the claim is released. In the volume section of your pod definition, simply refer to the PVC and mount a local folder on it. A persistent volume can have these states: available, meaning that the resource is free and not currently in use; bound, the volume is bound to a claim, so it's in use, it's not available anymore; release, the claim has been deleted, but the resource is not yet reclaimed by the cluster; and finally, failed. Well, something's wrong. Here's a cheat sheet for the PV and PVC commands. Using a YAML file, you can create either a PV or PVC by using kubectl apply-f and the name of the YAML file. You get the install persistent volume using kubectl get PV. The claims using kubectl get PVC. You can describe them, kubectl describe PV or PVC with their name. You can delete them using their YAML file, kubectl delete-f and the name of the YAML file, or by using their name, so kubectl delete PV and the PV name or the PVC name. And this concludes this section as the static way. Next, we'll take a look at the dynamic way. In this lab, we will create a persistent volume claim, and use a pod to mount a local folder on that storage. We will create that in Docker Desktop locally using the hostpath plugin. All right, so let's first take a look at the persistent volume YAML file. The kind is persistent volume. We give it a name, PV001, and a storage capacity, 10 megabyte, access mode, read write once, and we set the persistent volume reclaim policy to retain, and use that hostpath plugin here and to map to a folder in the Docker Desktop virtual machine to data here. All right. Let's take a look at the PVC. Kind, persistent volume claim. We give it a name, my claim. Read write, access mode must be the same as the PV, persistent volume. So let's double check. Read write once on the PV, read write once on the PVC. Awesome. We request 10 megabyte of storage, so we request the full capacity. We could have chosen a lesser value if you want. All right. Let's take a look at the pod now. So it's the kind of pod. It's a busy box. And we make a reference to the claim here in the volumes section. We give it a name and we reference the persistent volume claim called my claim. This guy here. Okay. And we use that name, mypd, and we mount it to a local folder called demo. We should see magically appear a folder called demo inside our busybox container. Okay, let's deploy our persistent volume. Right. Persistent volume PV001 created. Awesome. Let's look at the PV. kubectl get PV. Name PV001, capacity 10 megabyte, read write once. Reclaim policy to retain. It's available. It's not claimed. Awesome. So let's now deploy the claim. The PVC. Persistent volume claim. My claim created. Awesome. kubectl get PVC. My claim, it's bound to the volume called PV001, capacity 10 megabytes. Read write once. And let's again take a look at the PV to see if something has changed. Yep, it's now bound. The status is bound to the claim called my claim running in the default namespace. Awesome. Awesome. So let's now deploy our pod. Okay, my busybox was created. Let's connect to it using kubectl exec, the name of the instance, so the pod -it, and the program we want to run. Haha, let's do an ls and see if we see a demo folder. And there it is. We have our demo folder. Let's cd into that folder and let's create a file inside. Cat, and we'll pipe that to hello.txt. Let's type hello world. If I can type, Control D to exit and save the file. Let's do an ls to see if the file was created. Perfect. Okay. Let's exit the session. And now let's delete the pod. Let's delete the pod by using kubectl delete -f pod. And since the busybox takes 30 seconds to shut down, we will force it to do it right away. We don't want to wait. Okay. Let's deploy it again. Well, kubectl ctl get the pods, no resource. Awesome. It's really dead. Let's deploy it again. Okay. Let's open a session. cd demo ls. All right, and let's get that file. Hello, a car. Cat, not car. Hello world. Awesome. It worked. Let's exit our session. Let's now do our cleanup. We'll delete our pod. And then we will delete the PVC. Right? And then the PV. So you can't delete the PV before the PVC. Well, you can issue the command, but the command will be in kind of a wait state until the PVC has been released. Let's continue our journey into persistence by looking at the dynamic way. So here's a new object, the storage class, and the storage class represents a storage resource that is available cluster-wide and is provisioned by the cluster administrator. You don't have to set a capacity, and it eliminates the need for the admin to pre-provision a persistent volume. Now, compared with persistent volumes where once a claim has been made, the remaining capacity becomes unavailable. Well, the storage class can support many claims, many persistent volume claims. So you first select the cloud provider storage service that you want to use. You create a storage class. So here, no need to specify a capacity. Then you create a PVC, the claim, that refers to the storage class. And now you specify the required capacity. And finally, you use the PVC in your pod and mount a local folder. Like a persistent volume, there's an important property that you must be aware of. It's the reclaim policy. Set at delete, all data will be lost when the claim is released. And it's the default value also, like the persistent volume. So be aware. If you want to keep your files when the PVC is released, you have to set the reclaim policy to retain. Again, the default value is delete. Again, 3 access modes possible, and they are set using the PVC, not the storage class. Read-write many, the volume can be mounted as read-write by many pods. Read-only many, the volume can be mounted read-only by many pods. And lastly, read-write once, the volume can be mounted as read-write by a single pod, and the other pods will be in read-only mode. Useful if you have a main worker that writes data and the other pods simply read the data. So, you first start defining a storage class, specifying the cloud provider driver with the provisioner property and additional settings in the parameters section. So refer to the storage provider documentation on how to create a specific storage class for their storage service. You then define a PVC, specifying an access mode and the storage capacity required. In this claim, the claim is for 5 gigabytes, but more PVCs can be created over that storage class. Then simply refer to the PVC in your pod definition and map a local folder on it. In summary, the main benefits of a storage class versus a persistent volume is that with a storage class, you don't have to define a capacity and multiple claims can be made. Here's a cheat sheet for storage class commands. So you create your storage class using a YAML file, using kubectl apply-f and the name of your YAML file. You get a list of your storage classes or PVCs using get sc for storage class and get PVC. You get the storage class information by using kubectl describe sc and the class name. You delete your storage class and PVC using kubectl delete-f and the YAML file name, or you delete your storage class using delete sc and the class name, or delete PVC and the PVC name. And this concludes this section about persistence using the dynamic way. Let's see how to store configuration values using config maps. In a previous lecture, we saw that it was possible to place configuration values directly in the environment section of a pod definition. But what if we need to change that value? Well, we have to edit the manifest and redeploy the container. Also, usually it's not a best practice to tie an object with its configuration. So how can we externalize these values? The config map object allow you to decouple and externalize configuration values. The key value pairs are then injected in the containers as environment variables. They can be created from YAML files, a series of text files, or even folders containing files. They are static, meaning that if you change the value, the containers that refer to these values have to be restarted to get these refreshed values. Using a YAML file, you define a config map and place the key value pairs in the data section. You can even specify multi-line values using the pipe character. In the env section, environment section of the container definition, you define an environment variable, and by using value from an config map key ref, you reference the config map name and the key as defined in the config map. So in the config map key ref section, name refers to the config map name and key refers to a key in the config map. Earlier, I mentioned that this is a static process, meaning that the values are injected when Kubernetes starts the container. This means that if you make a change to a config map value, inside the container, the original values stay the same until you restart the container. To get around this, you can map a volume on a config map. Yes, you heard it right. Mounting a volume. This solves the static issue, and updates are reflected in containers. Each key value pair is seen as a file in the mounted directory. So we start with a config map, then use a volume to mount it to a local folder inside our pod, our container. The result is that all key value pairs are now seen as file, the name of the file being the key and the value being inserted in the file. While this sounds cool, it also means that you'll have to refactor your code. So instead of reading environment variables, you'll have to read files. So is it worth it? You'll have to figure out that by yourself. Here's the config maps cheat sheet. So if you're adventurous, you can create a config map from the command line. That's the imperative way. By using kubectl create config map, you give it a name, and with the from-literal parameter, you specify the key value pairs. So you can specify multiple key value pairs on the same line. Or you can use a good old YAML file and use kubectl apply -f and the name of your YAML file. You can create a config map using kubectl create cm, specifying a name, and specifying the name of a text file containing multiple key value pairs. Also, you can create a config maps from a folder. So if you have multiple files inside your folders, you can create a config map from that. You can get a list of the config maps by using kubectl get cm. You can output the config map in a YAML file by using kubectl get cm, the name of the config map, and the -o parameter with the YAML. And you can pipe that to a file name. And of course, you delete a config map by using its YAML file, using kubectl delete-f and the name of the YAML file. And this concludes this look at config maps. In this app, we're going to create a config map and use a pod that will reference a value stored in that config map. Let's take a look at the config map. So the kind is config map. We have a name, cm-example. And in the data section, we have two key value pairs, state, set to Michigan, and city, Ann Arbor. All right. So let's now take a look at our pod. Kind is pod. It's a busy box. And here in the environment section, we declare an environment variable that we will call city. And we are getting the value from a config map key ref, right? And we specify the name of the config map. So cm-example, that's the name of the config map. And the key is city. So here, that's the key right there. Okay. Again, environment section. We define a new environment variable that we will call city. We get the value from config map key ref, specifying the name of the config map and the key. Awesome. Let's create our config map. Okay. kubectl get cm to get information about our config map. So cm example to data. Okay. That doesn't give us much information, well, about the data itself. So let's do a kubectl describe config map cm example. Okay. We have the name, the namespace where it is, any labels and annotations. And here we have the data section, city Ann Arbor, state Michigan. And if for some reason you want to output that as a YAML, kubectl get config map, the name of the config map, -o output in YAML. To recreate the config map using this. Let's now deploy the pod or busybox. Perfect. Let's open a session. kubectl exec mybox -it and the program you want to run. And let's display the city environment variable. Let's echo that. Echo $city. And there it is, Ann Arbor. So that worked. So now I can type exit. And we can do a little bit of cleanup. We can delete our config map. And we can delete our busybox pod. Let's see how to use the secrets object. In Kubernetes, you will find many types of secrets types. The default one is the opaque type, and it is very similar to the config maps object that we saw in the previous lecture. You can also store credentials to connect to private container registries, authentication secrets, and even certificates. In this lecture, we will focus on the opaque secret. Like config maps, secrets are used to store configuration values, so they are somewhat identical to config maps, except that they store values as base64 encoded strings. And it's important to understand that base64 is a way to encode strings, and it is not an encryption algorithm. This means that secrets stored in Kubernetes can be decoded quite easily. Yeah, great. Since these secrets are not very secret, should you use them? Well, the answer depends on the type of information you want to store. It might be okay to store a connection to a database, but it might not be for something more sensitive. You can protect secrets using role-based access control policies, RBAC, or you can store them elsewhere. All cloud providers offered ways to store secrets in secure vault services that you can retrieve from Kubernetes. You can also use a third-party tool like the very popular Vault product from Archicop. Just be aware that the Kubernetes default secret, the opaque one, is not encrypted by default in Kubernetes. So you can define a secret in a manifest and use base64 encoded strings as the values, or use the command line where you can use plain text strings. Easier. In the pod definition, you simply get the secret value using the secret key ref section. This is very similar to config maps. And again, similar to config maps, you can mount a volume on top of secrets. Here's the container registry secret. You can define it using a YAML file or with the CLI. Next, in the pod definition, you reference the credentials in the image pool secrets section. Here's a cheat sheet for secrets commands. So you can create a secret the imperative way at the command line if you want, using kubectl create secret generic and then the secret name, and you pass the key value pairs with the from-literal parameter. You can of course create one using a YAML file, so kubectl apply-f and the name of the YAML file. You can get a list of the secrets using kubectl get secrets. You can output a secret to a YAML file by using kubectl get secrets, the secret name, and the -o YAML parameter, and you can pipe that to a file. You can delete the secret using a YAML file or using the secret name using kubectl delete secrets with the secret name. And this concludes this look at secrets. In this lab, we'll create a secret, and from a pod, we will reference secret and use them as environment variable. Let's take a look at our secrets.yaml file. The type or the kind is secret. We give it a name, secrets. And in the data section, we have key value pairs. So username to some value and password to some value. Notice that the values must be base64 encoded. You cannot put a non-encoded string here. How do you do that? On Windows, base64, the tool is not installed by default. So you can use these two websites, base64encode.org, decode.org, or you can install base64 using Chocolatey. Choco install base64. On Mac or Linux, well, it's already installed, so you simply do something like that. You echo your string and you pipe that to base64, and that will encode the string. And let me copy that and to decode echo the encoded string, and you pipe that again to base64-d for decode, and voila. All right. From the pod now, let's take a look at our pod YAML definition. The kind is pod, it's a busy box. And here in the environment variable, we're creating two environment variable. The first one is called username, and it gets its value from a secret key ref. And the name references the secret name here. And the value, well, the key is one of these two. So username or password here. In our case, key reference here, the username from the secret's secret. And second one is password. The environment variable is called password, and we get the value from the secret's secret, and the key is password. Awesome. Let's create the secret. All right. Let's get a list of the secrets. Here's our secret. It has two data. It was created 6 seconds ago. We can describe it. kubectl describe the object type and then its name. And here, what do we have? The name, namespace, and well, we don't see the secret, just the keys here. And what if we use kubectl get secrets and output that to YAML? Secret data password. See? Doing a describe would not allow us to see the values, but using get secret and outputting that to a YAML will allow us to retrieve the actual values. Okay. Let's now deploy our busybox. Right. Let's open a session. And let's echo username, the username, and the password. Whoops. Echo password, my password. So that worked. The values, the secret are decoded when they're injected into the pods. Let's exit that and let's delete our secret. And let's delete our busybox. Let's talk about observability. If you deploy a container using a deployment and it crashes, Kubernetes will create a brand new instance of the pod. This works because Kubernetes monitors the infrastructure. But what about your application? If your app crashes, well, Kubernetes will look at the pod health and see that it's still running. So from the infrastructure point of view, everything's working fine. Your pod is still up and running, but your code inside the pod has crashed. Would it be nice if Kubernetes could monitor the application health? Well, you can achieve this by configuring probes. The startup probe informs Kubernetes that the container has started and it's now okay to send traffic to it. The readiness probe informs Kubernetes that the container is now ready to accept traffic. Let's say that when your app starts, it needs to execute a series of steps like getting some configuration values from a database, creating some files, and so on and so on. And let's say that this startup sequence takes around 30 seconds. So even if your container is up and running, your code is not ready to accept traffic. So, using a readiness probe, you tell Kubernetes to wait 30 seconds before starting to send traffic. Lastly, the liveness probes tell Kubernetes if your app is still running, and if not, Kubernetes will kill the pod and replace it with a brand new one. Here's a pod definition with the 3 possible probes. The startup probe tells Kubernetes to wait for 10 seconds before making an HTTP call to a page called health. The failure threshold tells Kubernetes to try 3 times. The readiness probe tells Kubernetes to wait initially 5 seconds before probing and making a TCP call on port 8080, and then check every 10 seconds. The liveness probe tells Kubernetes to wait initially for 15 seconds before probing by making a TCP call on port 8080 and then check every 20 seconds. Note that the readiness probe will run during the whole pod lifecycle. But will these two conflict at some point? Yes and no. They will run simultaneously, but a failed probe will result in different actions from Kubernetes. Failing a readiness probe will tell Kubernetes to stop sending traffic to the pod, but the pod is still alive, right? While failing a liveness probe will tell Kubernetes to restart the pod. How does Kubernetes probe the containers? The kubelet will do the probing using the method you configured. With exec action, Kubernetes will run a command inside the container. With TCP socket action, Kubernetes check if a TCP socket port is open. And with HTTP GET action, Kubernetes perform an HTTP GET. Here's an exec action. You're telling Kubernetes to run a cat command on a file called healthy in the TMP folder. Here's a TCP socket action. You're telling Kubernetes to check if there's an open socket on port 8080. And finally, an HTTP GET action. You're telling Kubernetes to do an HTTP GET on the health page on port 8080. And this concludes this look at observability. In this lab, we will set a liveness probe. So let's take a look at our YAML file. We will deploy a pod that we'll call liveness-example. Is going to be a PC box. And this is where we're setting the probe. Type is liveness probe. We're asking to do an exec to run a command inside our container. And the command is cat, and the parameter is that file. So under the TMP folder, the file is called healthy, no extension. Basically, we're asking Kubernetes to run that command. If that command is successful, if the file exists, well, the probe is successful. If the file doesn't exist, the probe will fail. Okay. Initial delay seconds, we're asking Kubernetes to wait for 5 seconds before starting to probe. And then period seconds to 5, we're asking Kubernetes to probe every 5 seconds. The last parameter is failure threshold set to 2. Basically, we're telling Kubernetes that the liveness probe will fail when 2 probes will fail. Now, for the purpose of this lab, we will set something a little bit funky, just so we're able to do this test. We're running a command when the container starts. It's Dutch, and basically this will create that healthy file. And then we're telling the container to wait for 15 seconds and then to delete that file. right? Just a little trick too, so we'll be able to quickly see the effect of a liveness probe. Okay, let's deploy our pod. And let's quickly do a kubectl describe pod. All right, successfully pulled the image. The container was created. Okay, so let's do that again a few times and we'll see what happens. Just rerun the command. Oh, liveness profile, cat can't open. Okay, 2 times over 5 seconds. And now Kubernetes is killing the pod. Awesome. And it's still killing. So you see that here the pod was in an unhealthy state here. So now it's in the killing mode. Oh, and then Kubernetes is pulling again the BusyBox image and starting a new one. Right? And then it's on LT again, and the process starts again. All right. Let's do our cleanup. Let's delete our pod and we'll force it. You don't want to wait for it to end. Perfect. Let's take a look at some dashboards. While it's fine to use a terminal to get a view of your cluster, you may wish to use a graphical user interface instead. Luckily, there are many options available. We will take a look at these 3 popular and free options: the Kubernetes dashboard, the Lens desktop application, and K9S, a dashboard that runs in a terminal. Let's start with the Kubernetes dashboard. It's a web UI that you can install as an add-on inside your cluster. It's not installed by default by Docker Desktop and also by most cloud providers. The rule of thumb is, if you don't need it, don't install it. A, because it runs inside the cluster, so you need to find a way to expose it over the internet. And B, well, because of that, it's a known vector of attack. That being said, the Kubernetes dashboard that you see the various resources deployed inside your cluster. Simply select the type in the left menu, and you can also edit them by clicking on the edit icon, and you can edit the YAML file and click on update to change the manifest file. Lens is a IDE that runs locally on Mac, Windows, and Linux, so you need to install it on your OS. On top of viewing the resources and editing the YAML manifest, you can also use a built-in editor and also a built-in terminal. Lens is maintained by Mirantis, and you can download it from this URL. Here's the overview dashboard that lets you see a resource count. Like the Kubernetes dashboard, you can select a resource, click on the Edit button, and edit the manifest directly in Lens. You can also type commands using the built-in terminal. K9S is a cool text dashboard that runs in a terminal, and you can install it on Windows, Mac, and Linux. It might sound strange to run a dashboard in a terminal, but this makes a lot of sense. K9S is super light, starts in an instant, and gives you a clean view of all your resources. You can get information about the cluster, the resources, and you can take or make a series of action like deleting a resource, viewing the logs. Here we have a list of the pods currently running in the default namespace. Want to view the services that are currently running? Simply type colon and type SVC to list the objects type. Pressing S while a pod is selected will open a shell. You can also set a port forward by typing Shift F. You can even see the pod logs. I really like this K9S dashboard in a terminal and use it all the time. And this concludes this look at the Kubernetes dashboards. In this lab, we'll take a look at Lens. So Lens is a free dashboard that you can install on Windows, Mac, and Linux. Here's the URL, k8slens.dev. Let's take a look at the website. From there, you can install it. It runs on Mac, Windows, and Linux. So you can download the setup files here. Or if you're using Chocolatey on Windows, you can use Choco install Lens, or Brew on Mac, Brew install Cask Lens. All right. I've already launched Lens here, and by default, it should take you to your Docker desktop cluster. If not, or if you want to select another cluster, click on the hamburger menu to the left and select Add Cluster. Lens will look at the kubeconfig file, and you'll be able to select your clusters from that drop-down list. So here I have my demo cluster in the cloud. So I can select that and click on Add Cluster. I can be connected to multiple clusters. Here's my Docker desktop. Here's my demo. So let me switch back to Docker desktop here. Okay. So first thing first, let's deploy something on our cluster. Here I have a YAML file. It's a deployment. We'll have 3 replicas of an image called Hello App. Okay, nothing fancy here. Let's deploy this. All right, and let me switch back to Lens here. Now, let's click here on Workloads and Overview. So we should see 3 pods running here, 1 deployment, and 1 replica set. I can either from the top menu select pod, or from this workload menu select pods here and the other type of objects here. So here are my 3 pods. I have 1 deployment and 1 replica set. If I click on an object, I get more information, labels, annotations, and so on and so on. So something that you would have at the terminal, at the command line, by typing kubectl describe replica set or deployment or pod and the object name here. But here it's presented in a nice UI. All right. Let's take a look at our pods here. Okay, let's see what we can do. Let's say we want to delete this one. So I can select it like this. And from the ellipse menu to the right, I can open that and select remove, right? Or I can remove it right there. Okay, let's do that. Remove item, hello, yep, remove it. And since it's a deployment, Kubernetes will create a new one automatically. Pretty cool. Let's take a look at the logs. We can see the logs from there. We can open a shell. So ls, pretty cool. Directly from that UI. If I click on edit, well, I can edit the manifest file and click on save and close. That will update that object. We cancel that. Close this. There's a built-in terminal, so by default you have a small icon here called terminal. If you click on it, if you click on this open button, that will open the terminal. So I can type command kubectl get pods, right? You can try to delete an object directly here. So let me copy this object name, kubectl delete pod, and let's paste that. We should see right away, we see something happening at the top of the screen. All right. What's cool is that if you have more than one cluster, you can switch between these clusters. So here, let me, just to prove it, let's do a clear and kubectl get the nodes. Okay, on Docker Desktop, I have only one node. Let me select my demo cluster, my terminal. Let me open it. There's no deployment yet, but let's just do a kubectl get nodes, and for sure I have 3 nodes in this cluster. That's pretty cool. Just by selecting the cluster, I can switch and have a terminal that is in the right context. Pretty cool. So I just scratched the surface. There's a lot more information that we can get, like configuration, the config maps, the secrets, what the network services that are installed here. I have a cluster IP service, storage, so the persistent volume claims, persistent volume, storage classes. So here in my cluster in the cloud, I have 4 storage classes defined for me, the namespaces, and so on and so on. All the information that you would get from the command line using kubectl, you get the same information, but from a nice UI. So once you're done exploring, don't forget to delete your deployment. In this lab, we will use K9s, a super great dashboard running inside a terminal. So you can get more information about the K9s at the website, k9scli.io. Here's the website. Nice logo. And you can look at the documentation and the how to install K9s from that website. If you're on Windows, you can install it using Chocolatey. So Choco install K9s. On macOS, Brew install K9s. And on Linux, take a look at the documentation. All right. Let's first deploy something in our clusters. Here in our YAML file, I have a simple deployment with 3 replicas of a simple container or image called hello app. Nothing fancy here. Let's deploy that right away. Okay. And let's open a terminal or command line, command prompt, whatever you name it. And let me type K9S. All right, let me stretch that a little bit. Well, it's super cool. It's a dashboard running inside a terminal. It's super light and gives you tons of functionality. So here I have my deployment. So I'm in the default namespace. You can look at my my deployment. I can enter on an object, get more information, type escape, go back. I have information about my cluster. I can issue some commands. So Control D, I can delete a pod. Let me do that. Let me kill that poor pod here. Are you sure? Yes. See, you have feedback, visual feedback of what's happening. The pod that I deleted was killed, was in the terminating state, and a new one was created right away. I can hit D to describe the resource, escape to go back, Control K to kill. I just deleted one, but I can do a Control K. There we go. I can see the log, so let's switch to the second one. Type L, and I can look at the logs. I can open a shell also by typing here the S letter, do an ls, right? Can type exit, go back. I can even configure a port forward. Pretty cool here. I can look at the YAML file also. Type escape. Here we have the pods that are listed, but if I type colon, I can change that. Let's say, let me type deploy. So here's my deployment. Now, if I type E, I will edit the deployment, and let's change the number of instances or replicas from 3 to 4. And let's close that. All right. And now I have 4 out of 4. So let's, I'll type colon again and type pod. Here are my 4 pods. Super interesting. It's a free tool. It's super light. It's super fast. And I always have one open so I can see visually what's happening inside my cluster when I'm issuing some commands. Let's go back to our page here, our Visual Studio Code, and let's simply delete our deployment. And let me switch back right away here. And they're gone. Pretty cool tool. Let's see how to scale pods. The horizontal pod autoscaler is a Kubernetes feature that allows you to scale the number of pods up and down. It uses the metric server to gather the pod's utilization. Pods must have requests and limits defined. The HPA checks the metric server every 30 seconds and scale the number of pods according to the minimum and maximum number of replicas defined. To prevent racing conditions, the HPA waits some period of time after a scaling event. By default, the delay on scale-up events is 3 minutes, and the delay on scale-down events is 5 minutes. In this pod definition, you specify the CPU and memory requests and limits. The request is what's allocated at first, and the limit is what you allow the pod to burst to. In this example, the pod will start with 64 megabyte of RAM, but can burst up to 128 megabyte if needed. You configure the HPA using a manifest specifying the deployment you want to scale, the min and max number of replicas, and the metric you want the HPA to scale on. In this case, we tell the HPA to kick in when the average CPU utilization is above 50%. Here's a cheat sheet for the HPA commands. So you can create one using the imperative way, using kubectl autoscale deployment, the name, and the metric and replicas number. You can create one using the YAML file. You can get the autoscaler status by using kubectl get HPA and the HPA name. And of course, you can delete the HPA using the YAML file or kubectl delete HPA with its name. And this concludes this lecture about scaling pods. In this lab, we will use the horizontal pod autoscaler to scale a pod. For the HPA to work, it needs some data, some metrics coming from the metric server. And by default, it's not installed by Docker Desktop. Let's just make sure. I'll open a terminal. And what we'll do, we'll get a list of the pods running in the kube system namespace. Core DNS, etcd, kube API server, proxy, provisioner. No, nothing that looks like metric server. Okay. To install it, you need to run this YAML file coming from this Git repo on Kubernetes-SIGs, special integers group, and metric server. But you need to make a small modification to it. Let's take a look at the components.yaml file. You need to edit it if you download it directly from the Git repo, and you locate the deployment section. There it is, deployment. And what you need to do is add this parameter, kubelet-insecure-tls. If not, the metric server will not run on Docker Desktop. All right, let's deploy our metric server, kubectl apply -f components.yaml. Awesome. What we can do, we can run again kubectl get pod in the kube system namespace. Aha, metrics server. There it is. It might take a couple of minutes for the metric server to start running. Now that the metric server is running, let's take a look at our deployment. It's a deployment, and what we'll deploy is a web server called hpa-example listening on port 80. So it's a simple web server that will return a web page, nothing fancy. What we'll do, we'll also deploy a busybox, and from that busybox, we'll hit that web server in a loop, and that should generate some traffic. Awesome. Let's deploy our web server. Let's get a list of the pods running in the default namespace. Awesome, it's running. Let's enable our autoscaler. So kubectl autoscale deployment called hpa-deployment on a metric called CPU%. And we want a minimum of 1 instance and a maximum of 4. Okay. Let's validate that we have an HPA, kubectl get HPA, that will list all the HPAs running on my cluster. There's only one. Awesome. Let's now deploy our busybox. And let's connect or open a session on that BusyBox. Perfect. And here's our endless loop that will hit the web server. That should generate some traffic. Okay, let's take a look at our K9S. I have my deployment here, my HPA deployment, and my BusyBox. And yeah, we have 3 instances of our deployment right now. Awesome. So the HPA worked. And now what I can do is stop the loop by hitting Control C. And I'll type exit to exit my BusyBox. And from there, I can delete my HPA. But be careful when you do that. I'll delete my HPA here. If we take a look at the deployments, there's still 3. Nothing will scale that down since the HPA has been deleted. So let's delete our BusyBox. And let's delete our deployment. That should delete all 3 instances. Let's take a look here. Yep, all 3 are terminating. And optionally, you can delete the metric server by using kubectl delete and the components.yaml file here. We are at the end of this Docker Containers and Kubernetes Fundamentals course. Congratulations! You are now an official Kubernetes ninja! The next steps for you would be to deploy containers in the cloud using services from a cloud provider. These courses will teach you how to do that on Google Cloud and Azure, and also on smaller cloud providers like Linode and DigitalOcean. The best part is that each offer free credit usage when creating new accounts. This way, you can create a managed Kubernetes service in the cloud without breaking the bank. If you enjoyed the course, you can help me by making a small donation. This is the link to my Buy Me a Coffee page. I want to say a big thank you for learning Docker and Kubernetes using my course, and I wish you all the best.